So if we follow along with our textbook and we look at the example that's given to us on page 235, example 8.1, looking at this example, it says the following. That a neuropsychological test, such as the Wisconsin card sorting test, can be used to measure conceptual thinking ability and mental flexibility. Performance on this type of test declines gradually with age. Suppose that previous researchers selects a test for which adults older than 65 have an average score of a population average equal to an 80. So here it's assuming that previous researchers have already done research and they've assumed here that the population average is going to be equal to a value of an 80. So if we look at this idea of our z-test, and remember here, if we again think about the types of hypotheses that are given to us, if we look at the null hypothesis is essentially predicting that z should be equal to 0. So in other words, if we're collecting data out of our own behalf from individuals who come from the same population, we're going to then assume that our average, right, so capital M, is going to be equal to the population average. So in other words, if we were setting up this particular example or this particular study in where we know that individuals already have a population average of an 80, but now I'm doing a research study and I make a small modification, and as the modification explains here in terms of the sample or in this example, that we are now providing supplements for individuals in terms of the exam, we would then assume here that if we look at our average, we would expect that our average would either be equal to or not equal to the population average equal to an 80. So if we look here at the null hypothesis and the alternative hypothesis that are given to us on page 236, you're going to notice that the null hypothesis predicts that our average, in other words, the average that we calculate from our study should be equal to the average that's already given to us by the population from previous research. So in other words, my average from my current study should be equal to the average from previous researchers. So in other words, the difference between my average and the population average should be equal to 0. So remember again, when we think about our formula for z, in this particular case, the way that we're doing it for hypothesis testing is that we're using capital M, my sample mean, minus mu divided by, in this particular case, it's going to be the standard error, and our standard error is going to be defined as sigma in this particular case, or what we just call standard error. If you look on page 241, you can see how it is that we actually calculate standard error. To calculate standard error, it's not very difficult. All you're going to do is you're going to take your standard deviation. In this particular case, it's assuming here that you had the standard deviation for the population, so that's why we use the symbol here of sigma, divided by the square root of our sample size. So in this particular case, whatever your sample size would be equal to, you would take your square root, that would be your denominator, divided by your numerator. In this particular case, it would be equal to sigma. So here, to calculate your standard error, this is the way that we would actually calculate that value. So what is standard error? Standard error, the way that it is defined in terms of your textbook, if you look on page 216 for chapter 7, even though I asked you not to cover chapter 7, I just do want you to look at the definition for chapter 7 for standard error. Standard error is defined as it provides a way to measure the average or standard distance between a sample mean and the population mean. In other words, the standard error provides a method for defining and measuring sampling error. So ultimately here, what we're going to do for standard error is that we're going to assume that we're going to be taking a specific number of standard deviations, and then we're going to be looking at the average distance between my mean and the population mean. So in other words, how much of a difference there is between my calculated average for my sample and the population mean. And if we take multiple samples from the population and we calculate the distance of my mean from the population mean, all of those averages or all of those distances would then be converted into an average, which then would be considered to be my standard error. So in other words, if I have a population, and let's say again, remember that my population is going to be 1,000 individuals. So here, let me just write out 1,000, and I take one sample, and my first sample has 200 individuals, and I calculate an average, and let's say my average is equal to a 2.2, and the population average, right? Let's assume here that we knew it. The population average was a value of a 4. We would then calculate the distance between 2.2 and 4. I would then take another random sample of individuals from that same population. Let's say that now we randomly sample 100 individuals in this particular case. Their average now is going to be a 3.1 in this particular case, and we calculate the distance between the population average and the sample average that we calculated. And we do this over and over and over and over again. And every single time that we calculate the distance between my average and the population mean, so in other words, my sample mean and the distance to my population mean, we would calculate then an average. So we would take all the number of times that those actually occurred, and then we would actually then divide by our number of occurrences or the number of samples that we actually took to then be able to define for ourselves the standard error. So in this particular case, for our purposes in terms of the course, do I need you guys to know how to calculate standard error? For our purposes, don't worry about this. The only reason I'm talking about standard error at this point is because it is used in your example here. But what's more important for us to understand is the conceptual rationalization that we're going to be talking about here in terms of what the value that we actually calculate for z is and how we actually compare it to a given value that we'd assume exists in our population, and thus then able to look at the difference between my score and that population average here that we're talking about, to then be able to draw conclusions if my value that I've calculated is extremely different from that particular value. So again, if you're still following along with us in terms of page again 235, if I'm not mistaken here, looking at example 8.1, here again our null predicts that my sample average minus my population average would be then equal to 0, right? Because there would be no difference between them. So it doesn't matter whatever my standard error is equal to, because 0 divided by anything is going to be equal to 0. So thus z would then be equal to 0 because the distance between my calculated average for my sample and the population average wouldn't be different. Now, the alternative hypothesis predicts the opposite of that, indicating for us that my average is not equal to the population average, so thus z would not be equal to 0. So in other words, in my numerator, we would have a value that is different. So in other words, my average minus my population average would be different from each other, thus not being 0 in the numerator. And again, it doesn't matter what my standard error is. It was just assuming here that the difference between my sample mean and the population mean are not going to be equal to 0. So thus, in our particular case here, remember that we have to assume that we're talking about a z distribution. So if you remember from our z distribution, so here I'm going to draw this out for us, it's a normal distribution that we were working with. And we would assume here that the mean for our z distribution is equal to 0. Now, in our particular case, even though our mean is equal to 0, let's just assume the following here. If I draw this other bar on top of our distribution, I'm assuming here that this line here also represents the population average equal to an 80. So in other words, remember that z-scores tell me how far my raw score is from the mean in terms of standard deviations. So here we would assume then that z equaling 0 would mean that your score is equal to the mean, correct? So remember our formula for z for our raw score calculations is x minus x bar divided by standard deviation. So here we would assume that the mean for my distribution that I'm working with is equal to a z-score of 0, because the difference between my score and the mean, if they are the same value, we would have a value that is equal to 0. So again, doesn't even matter what standard deviation would be equal to in this particular case. My numerator would be equal to a value of a 0 because my score would be equal to the mean. Thus, the distance between those values would be equal to 0. So I'm assuming here that since my population average is equal to an 80, this line here represents an 80 here for the population mean. We just label it as 0 because this is in reference to our z distribution here that we're talking about. Okay, so here you can actually see an example of this exact same graphical representation that I'm making here on page 239 in your textbook for figure 8.5. So this would be figure 8.5 in your textbook, where we actually have the exact same representation here that we're looking for. So in other words, we have the 0 being represented here for the mean for my z distribution, but it is a representation of my population average equaling a value of an 80. So now what I want to know is I want to know the following. So if I go out and I collect data, and I collect data with my sample of individuals, will my average for their performance on whatever it is that I'm measuring them on in this particular example, will my average equal a value of an 80? So the distance between my average and the population average, will there be no difference between those values, thus indicating that my score is equal to a 0? Or will my mean not be equal to a value of an 80, and thus then I have to then conclude, is my average extremely different from a value of the population average in this particular case? Okay, so that's ultimately what we're trying to identify in our particular situation. So again, we're here in step number 3. So when we're going to test my statistic for significance, and in our particular case, what statistic am I talking about? I'm talking about the z statistic here that I calculated for this particular example. So remember here, again, I'm calculating the average for my group minus the population average divided by our standard error in this particular case. So ultimately what I want to do is I want to know what my z value, or where my z value lands on what we're going to call a sampling distribution. So in other words, what we're drawing here, this distribution here, even though we do call it a normal distribution, we're going to call this a sampling distribution. Okay, so this is my sampling distribution. Now this sampling distribution assumes some of the following assumptions. One of the very first assumptions that it assumes that the null hypothesis, so H0, is true. So why does it assume that the null hypothesis is true? Well, remember that we talked about this point for null hypothesis significance testing. Why do we test the null hypothesis for extreme testing, in other words, right? Because that's what the term significance really means for us. So why do we test the null hypothesis? Because it provides me with the value of a 0. Because remember, it's telling me that z should be equal to 0. So in this particular example that we're working with, for example, 8.1, it's predicting, right, the null hypothesis predicts that my group average that I've calculated, no matter what it is that I do to them, right? So it doesn't matter if I've included another manipulation, it doesn't matter if I'm giving them supplemental materials to read, it doesn't matter if I'm letting them watch YouTube videos, nothing matters here, because it's assuming that no matter what you do, your group average is going to be equal to the population average that's already been calculated by other researchers. Thus, my group average should be equal to a value of an 80 in this particular example. So here, z, the difference between my group average and the population average, would then be equal to 0 in this particular case. So since I know that the null hypothesis predicts a 0 for me, we have to assume the following. So today, the null hypothesis predicts that the difference between my group average and the population average would be equal to 0. Tomorrow, I do another study. It assumes again that my average minus the population average would be equal to 0. Third day, same thing. Fourth day, same thing. 1,000 days in a row, the null hypothesis always predicts a 0. So 0 divided, let's say, by 1,000, in this particular case, is going to give me an average equal to a 0. So thus, the mean for this sampling distribution is equal to a 0 because I have to assume that the null hypothesis is true, and I have to find some central point here that I can use as a reference. And here, the only value that I know that potentially exists anywhere out there in my theoretical world for the population is my value of 0, because the alternative hypothesis doesn't give me that information. The alternative hypothesis only tells me that the value should not be equal to 0, but I don't know what that reference point is. So here, I need to know what that reference point is. It has to be that value of 0. So here, on this sampling distribution, I have to assume that the null hypothesis is true. Now, whenever it is that we do null hypothesis significance testing, we also sometimes call this NHST. So you'll see this in your textbooks from time to time, NHST. All that refers to is null hypothesis significance testing. We're going to do null hypothesis significance testing pretty much for all inferential stats. So for all inferential statistics. And there are going to be some stats that we are going to be doing null hypothesis significance testing that are not necessarily inferential stats. So for instance, we're going to do this for our correlation coefficient later on in the semester, which is a descriptive statistic and not an inferential stat. But here, we pretty much do null hypothesis significance testing for all our statistics that are inferential in their nature. So in other words, the ones that are going to allow us to draw conclusions about the null and the alternative hypothesis. So in other words, the statistics that allow me to draw conclusions about the population. So here we're going to do this, in a couple of weeks for T. We're going to do this for F stat. Right now we're doing it for our Z statistic, etc. So we're going to be testing our statistics for significance. So all of these statistics assume a distribution that is very similar to this. The only one that's a little bit different is my F distribution, and when we get to the F distribution, I'm going to show you that it's actually positively skewed. So there it'll be just a little bit different, but ultimately T, Z, and R assume a distribution that looks just like this, that is a normal distribution. It is unimodal, it is symmetrical, it is not skewed, it is not kurtotic, it meets the proportionality requirements of normality, so thus it is normal. So here, this sampling distribution, what is a sampling distribution? A sampling distribution is defined as a distribution of statistics. So I'll say that one more time. So a sampling distribution is a distribution of statistics. What does that mean? Well, a distribution of statistics ultimately means that on this distribution here that I'm looking at, I have to assume that they all represent the exact same statistic. So in other words, all values on this distribution represent the same statistic. So in other words, it assumes in this particular case, since I'm talking about Z, I'm looking at the difference between my sample average and the population average. I'm assuming here that I'm going to calculate a Z value in that particular case. So here, I'm going to assume that this is a Z sampling distribution. So in other words, on this distribution, we're only going to have Z statistics. Okay? We are not going to have T stats, F stats, R stats, beta stats, or any other types of statistics that you want to think about. Here, all that we're having is we are talking about Z statistics. Why? Because the Z statistic in this particular case assumes a very specific role. So traditionally, we had been thinking about Z, looking at the difference between my raw score and the sample mean divided by standard deviation. Now, the way that we're looking at it here is essentially my sample mean minus my population mean, that I would have to know what that value is, divided by standard error in this particular case. So here, it assumes that it's looking at the distance between my mean, my sample mean, and my population mean. That's a very different assumption than what T does. T statistics, for instance, that we're going to learn about in a couple of weeks, compares two groups that are mutually exclusive or related to each other. So it compares the sample averages to each other. So the average for group 1 and the average for group 2. F compares 3 or more groups. R looks at the relationship between continuous variables. Z is looking at something completely different than any of these other stats. So it's not fair for me to compare my Z statistic to my R stat, to my S stat, or to my T stat, because they have very, very different assumptions. Okay? And that's a very important thing to always consider. That if I calculated a Z statistic as my test statistic in this particular case, I now am wanting to use my Z-stat that I've calculated and compare it only to other Z statistics. Think of the following situation. Think of you taking an exam for a statistics class with me and then comparing yourself to someone else who took an exam for statistics with a different professor. Would that be fair to compare yourself to the other person? The answer should be no. Why? Because that other person comes from a whole completely different distribution. They come from a distribution where their professor is X, Y, and Z. And for your distribution, your class, your professor is me. right? So it's not fair to compare each other across different classes if they are different professors, they're different books, they're different exams, they're different materials, etc., etc., etc. So here, the same thing is going for us in terms of statistical testing. What I'm trying to do is I'm trying to compare my statistic that I've calculated to other statistics that are similar to it. So I calculated a z-stat. I now want to compare my z-statistic to other z-statistics that exist. Okay? And that's a very important thing that we all have to understand. So in our particular example, if you're following along in your textbook, if we're now on page 241, you'll notice here that in our example, it assumes that the sample average that we calculated is an average of a 92. Okay, so it's assuming here that when we did our research study and we calculated an average for our particular group of performance individuals, we calculated an average of a 92. Remember that previous researchers had told us that my population average, so mu, should have been a value of an 80. So now what we want to do is we want to calculate my z-score for my particular study. So using the formula here that I've already given to you a couple of times, for this particular type of example, here I have my average of a value of a 92 minus the population average of an 80. And in this particular case, the standard error for this example is a value of a 4. And the reason that we calculate that value of a 4 is if you look at the top of page 241 for the way that they calculated standard error in our particular case, remember that standard error is calculated by the standard deviation of the population divided by the square root of our sample size. So our sample size was equal to a value of a 25. It was already given to us that the population standard deviation was equal to a value of a 20. So in this particular case, 20 divided by the square root of 25, which would be equal to 20 divided by 5, would be equal in this particular case to a value of a 4. So that's where we get our standard error equal to a value of a 4. So remember, what is our standard error? Our standard error is assuming here the average distance between my average and the population average if we took an infinite amount of samples and we calculated an average distance. So in that particular case, something very similar to like a standard deviation that we would actually want. So in other words, the distance between, in this particular case, my average and the population average, so that deviation, so that particular average, that's why we call it a standard error in that particular instance. So here, once we do our calculations, so looking at the difference between 92 and a value of an 80, so 92 minus 80 in our particular case is going to give us a value of a 12 divided by 4. In our particular case now, 12 divided by 4 is going to be equal to a z-score equal to a value of a 3. So in other words, now what we want to try to do, and this is a positive 3, so always remember to put your positive or negative signs. So now what we want to do is we want to say the following. Okay, I know that my null hypothesis predicts that z should be equal to a value of 0, right? I calculated in my particular study a z-score looking at the difference between my sample mean and the population mean. I calculated a z-score equal to a value of positive 3. So now what I want to do is I want to know, is my value of a positive 3 extremely different from this value of 0? Now remember, this goes back to my previous example that I was telling you all about my colleague who was working at that institution where they said, okay, well, we have 14,000 people one semester. In another semester, they have 14,010 people. Is the difference of 10 individuals really an extreme difference? And he said no, and I said no, and a whole bunch of other people said no. But some individuals looked at those raw numbers and said, absolutely, there's a difference there. You all are crazy for saying that there is no difference. The numbers go up. So we absolutely are different. So here now what we're trying to establish is we're trying to say, look, is the difference between my number here that I've calculated for my study and this base number that's given to me by the null hypothesis, are my numbers extremely different from each other or not? That's really what we're trying to get at here in terms of our particular example. So now what we're going to do is we've already gone ahead and we've calculated all our statistics that we need. We've drawn out my sampling distribution as we've done right here. And in this sampling distribution, where we assume that the null hypothesis is true for a z distribution in this particular case, because remember, I want to compare my value that I've calculated, which is a z-score, to other scores that are similar to it, in other words, other z-scores, because I don't want to compare it to other things that don't relate to it or that are not similar to it. So here, this is z equals a value of a 0. So now I want to identify on this distribution where my value of a z equal to a 3 is going to land. Okay? Now, one of the things that we have to think about on terms of the sampling distribution in terms of null hypothesis significance testing is that for us to identify if there's an extreme difference between my calculated value and the proposed value given to me by the null hypothesis, I have to, on this sampling distribution, identify what are called regions of rejection. What are regions of rejection? Regions of rejection are what we also sometimes call critical regions, so sometimes you'll see them called critical regions. Both of them are the exact same thing. So if I ever use the terms interchangeably, don't think to yourself, oh man, where did he get these critical region things from? It's the exact same thing as a region of rejection. A critical region or a region of rejection is that area on a sampling distribution where if my statistic falls within that region, I'm going to reject the null hypothesis. Okay? So I'll say that again. So very important. I'm repeating myself here. So this is critical information for us. Right? That's a joke because it's critical regions, right? Okay, sorry guys. I know. I like making stats jokes. And hopefully you guys are starting to get an appreciation for statistical jokes, right? Because I try to make them all semester. Okay, so critical region or region of rejection, that area on a sampling distribution where if my statistic falls within that region, I'm going to reject the null hypothesis. What does that mean? Okay, essentially remember, what does my null hypothesis predict? My null hypothesis predicts that z should be equal to 0, that there should be no difference between my sample mean and my population mean in this particular case, right? No difference, no effect, no relationship. That's what the null hypothesis predicts. So now I'm saying, look, on this sampling distribution, I'm going to find where I can now reject that statement. Okay? Why do I want to do that? I want to have that area on this sampling distribution where I can reject the statement made by the null hypothesis, because if my score is actually extremely different from 0, I want to be able to say, hey, there seems to be a difference between my z-score and the proposed z-score given to me by the null hypothesis, thus leading me to conclude that the difference between my average and the population average in this particular case are extreme. That's a real difference. That's ultimately what I want to conclude. Okay? The only way I can conclude or make that judgment call is if my statistic of a value of a 3 in this particular case lands inside of the region of rejection. If my statistic lands outside of the region of rejection, I am not going to be able to reject the null hypothesis. I'm going to have to retain the null hypothesis. In other words, I'm going to have to say, okay, there is no difference between my z-score and the z-score of 0, thus there is no real difference between 92 and an 80, okay? That's ultimately what it's boiling down to. That's what I'm trying to really conclude about. So here, what's the purpose of null hypothesis significance testing? The purpose of null hypothesis significance testing, if you want to put a star next to my statement here, the purpose of null hypothesis significance testing is ultimately to look to see if my statistic is different from the proposed 0 statistic given to me by the null hypothesis, and if my statistic is extremely different from that 0 value, I'm going to conclude that the groups differ, there is a relationship, or that there is an effect. Okay? If my statistic does not land inside of that region of rejection, it lands outside of that region of rejection, I'm going to have to say that the difference between a 92 and an 80 is not a true or extreme difference. There's a difference between the numbers, right? There's a quantitative difference between those numbers, but it's not an extreme difference. So again, going back to our example of you saying that you got an 81 and somebody else saying that they got an 80 on the exam, are you really that much more knowledgeable in terms of your course than this other person? And the answer should probably be no. Why? Because the difference between these two numbers is so small. But the only way that I can tell if this difference between these numbers is real or not is if I calculate an inferential statistic, right? Not just looking at the difference between these numbers. I have to calculate an inferential statistic, see where my statistic lands on this distribution associated with its specific type of stat. So in other words, if I calculate a t-stat, I would calculate other t-statistics. If I calculate an f-stat, I would compare it to other f-statistics. An r-stat, compare it to other r-stats. If I calculate a z-stat like I am here, I'm going to compare it to other z-statistics. So here, ultimately, what am I trying to conclude? I'm trying to conclude if the difference between 92 and an 80, which comes out to being a z equal to a 3, right? So here I did not just compare my averages, I had to calculate my statistic associated with that. So here I've calculated my statistic, and now I have to compare this statistic to the zero value that's given to me here to see if it is extremely different. That's the purpose of null hypothesis significance testing. Okay? Now on this sampling distribution, I have to identify regions of rejection. Regions of rejection, again, that area on a sampling distribution where I'm going to be able to reject the null hypothesis if my statistic falls within that region, depends on a couple of factors. The regions of rejection are going to depend on what we call alpha level, sample size, and also this idea of a one or a two-tailed design. Okay? So again, regions of rejection or critical region is going to depend on alpha level, one or two-tailed design, and sample size. So alpha level, one versus two-tailed, and sample size. There we go. One versus two and sample size. Those are the three factors that are going to affect the region of rejection. Why are they going to affect the region of rejection? Because they're going to affect what we call a critical value. The critical value is defined as the following. The value that indicates the start of the region of rejection. So the critical value indicates for us the start of the region of rejection. So in other words, how do I find out where my region of rejections begin here on my sampling distribution? I have to find my critical value. What is my critical value? My critical value tells me where my regions of rejection begin. What is my critical value dependent on? It's dependent on alpha level, if it's a one versus two-tailed test, and also sample size. So you'll notice here, I've spent the last 30 some odd minutes talking about point number 3. Is point number 3 important? Yes, it's highly important. It's extremely important for us. That's why I'm spending so much time here. If I can make a recommendation for you in terms of trying to understand null hypothesis significance testing better, I would recommend looking over this part of our lecture over and over and over again, trying to understand conceptually what it is that we're doing here. So ultimately, again, I've calculated my statistic. I'm now comparing my statistic to the zero given to me by the null hypothesis. And now I want to identify if this value that I've calculated falls inside this region of rejection, so I can either reject the null hypothesis or I can retain the null hypothesis. So again, if this stat lands inside of the region of rejection, it's going to suggest to me that this number here is extremely different from that zero value, thus indicating that the difference between 92 and 80 is an extreme difference. If my value does not land in the region of rejection, I cannot conclude that the difference between a 3 and a 0 is extreme and that the difference between 92 and an 80 is extreme. Very, very important. Very, very important conclusions here that we're drawing. Now, to make this a little bit easier for me, I'm going to open up just a document here so that way I can draw a little bit because I'm going to draw quite a bit. So I want to make sure that I'm able to do this appropriately for us to be able to view. So give me a second here. All right, so now let's start working on this idea. Let's start working on this idea of how it is that we come to the conclusion that my statistic landed in the region of rejection. So in other words, how do I identify, so how do I ID my critical value? And why? Because I want to identify my region of rejection, or what we call my critical region, right? So that's what I want to do. So how do I identify my critical value? Because what I want to do, and again, remember, I have this sampling distribution here where we have a zero value, right? Because again, this is assuming that the null hypothesis is true, so the null is true. So here I have to assume that my zero value is the average in this particular case. So now on this sampling distribution for Z, right, in this particular case, so Z sampling distribution, where the null hypothesis is true, I want to now identify where my regions of rejection are. Okay, that's what I want to do. So how am I going to do this? Again, remember, I need my sample size, I need my alpha level, and I also need to know if it's a 1 versus a 2-tailed test. Okay, so here, let's define a couple of terms. So sample size, we already know what we're talking about. We've been talking about sample size all semester long. Alpha level, very, very important. What is alpha level? Alpha level is defined as the following, and I don't like the way your textbook defines it, and I really, really hate it, to be honest with you, and I wish they would change the definition. They actually use the right definition or the better definition later on in the chapter. So if you look at the definition on page 238, I would recommend not really following along with that definition here that they use, because it says alpha level or level of significance is the probability value that is used to define the concept of very unlikely in a hypothesis test. If you're trying to figure out what that means, I don't even know what that means, to be honest with you. I read that 100 times. I was like, I don't know what you're talking about, because that doesn't fit into what my definition is of an alpha level, because this is the right definition of an alpha level. And you'll find it on page 244. So you'll find it there under the definition of type 1 error. What is alpha level? Alpha level is the probability of committing a type 1 error. That is what alpha level is, the probability of committing a type 1 error. What is type 1 error? Incorrectly rejecting the null hypothesis. So that's what a type 1 error, incorrectly rejecting the null hypothesis. In other words, type 1 error is when we say, yes, there's a difference between my sample mean and the population average, when in reality, there was no difference between them. In other words, just like in the case with my colleague, where he said, well, we have 14,000 students, now we have 14,010 students. People assumed here, yes, there's a difference between the groups, when in reality, there was no difference between the groups. But people here were saying there is a difference between the groups, there is an extreme difference. So here what we're trying to do is we're trying to avoid making that mistake where we say, yes, there's a difference between groups. In this particular case, yes, there's a difference between my sample mean and the population mean, when in reality there is no difference. So again here, I don't want to make the mistake of someone saying, well, I got an 81 on the exam, somebody else got an 80. Well, the person who got an 81 is way smarter than the person who got an 80. They are extremely smarter, or they're extremely more knowledgeable than a person who got an 80 on the exam. To be honest, that's not true, right? Because here, is that difference really an extreme difference? No, probably not. What's that difference probably due to? It's probably due to something like error variance that we've talked about all semester long. So in other words, differences between my groups or between my scores that are not due to the researcher's manipulation or control. So that's what we're trying to do here in this particular case. So I don't want to make that mistake. I don't want to make the mistake where I draw the wrong conclusion. I'd rather be a little bit more conservative and say that there is no difference between these groups, even though there may be a difference. But in reality, I still want to try to avoid making that mistake. Now here, you're going to find in your textbook where it indicates something that's also called type 2 error. What is type 2 error? This is the probability, type 2 error is incorrectly retaining the null hypothesis. So in other words, I should have rejected the null hypothesis, but I didn't. So in this particular case here, with alpha level, so the probability of committing a type 1 error, so incorrectly rejecting the null hypothesis, here, this is what should have happened. Your stat should land in the region of rejection, okay? And your stat should not, apologize. So stat should not land in the region of rejection. But yet your statistic did land in the region of rejection. So with type 1 error, your statistic should not have landed in the region of rejection, yet it did. How does that happen? So how is it possible that your score that you calculated might have landed in the region of rejection? Okay, so let's think of the following situation. Let's say that you're the one who got an 80 on the exam, and somebody gets a 90 on the exam. Is that an extreme difference between the two? We would all probably conclude that yes, there's a pretty big difference between those two numbers. But now, let's say that we really sat down with this person who got a 90, and we talked to them, and we gave them an oral exam rather than a written exam. And we find out that this person, in reality, their true score should have been equal to a value of an 80. Okay? But yet, they reported a 90. So how is that possible? How did somebody report a 90, but yet their true score is an 80? Well, maybe this person cheated. Maybe this person sat there with their textbook and they answered the questions on the exam. Or maybe somebody else gave them the answers. So in reality, it looks like if there's a difference between your scores. So if we were to calculate a statistic and to identify if my stat lands in the region of rejection or not, more than likely here, my stat would have landed in the region of rejection. Should it have landed in the region of rejection if this is what the true score was? The answer is no. It should have not landed in the region of rejection. But yet here, I still concluded that there was a difference. So I concluded that the scores differed because these are the scores that are reported to me, because again, me as a researcher, I don't know if someone's lying to me or not, right? I don't have time to sit down with everyone and identify if they're lying to me or not. So here, rather, I look at those scores that are reported to me, I conclude that there's a difference between them, and I say, hey, your statistic landed in the region of rejection. So I'm going to go ahead and reject the null hypothesis. Unfortunately, though, I incorrectly rejected the null hypothesis. My statistic should have never landed in the region of rejection in that particular case. Why? Because the person's true score was a value of an 80, not a value of a 90. Now for type 2 error, which is incorrectly retaining the null hypothesis, in other words here, your stat should have landed in the region of rejection. So your statistic should have landed in the region of rejection, but it didn't. So in other words, you are saying, no, the groups don't differ, when in reality they should be differing. Why may that happen? Well, for a variety of reasons. Maybe somebody figured out what you were trying to do in the experiment and they were messing with you and they reported lower scores than what they actually reported. So in other words, let's say here that someone doesn't get a 90, but they report an 81. Oops, there we go. So they report an 81. Their true score should have been a 90, but they report an 81. Why? Well, because maybe they didn't want to make other people feel bad. Maybe they didn't want to mess up the curve if they were going to curve grades for the exam. Who knows? So ultimately here, the person should have gotten a 90, but they report an 81. So now it looks like if there's no difference between an 80 and an 81, when in reality there should have been a difference between an 80 and a 90. So potentially there, the difference makes it look like if it's non-existent, when in reality there should be an existent difference. So here you can see that with statistics, there's lots of different ways that we can mess up. And there's lots of different ways also that we can kind of manipulate our data to make it look like whatever it is that we really want to in some particular cases. Okay, so that's alpha level. Now, if you looked on my notes for the presentation, in the presentation I say here, alpha level is equal to 0.05. What is this value of 0.05? Well, that value of 0.05 is essentially the percentage that we give for alpha level. So in other words, we are saying the following. We're allowing you 5% or 0.05, right? we give you a 5% probability of incorrectly rejecting the null hypothesis. So in other words, we give you a margin of error. Okay? Why do we give you a margin of error? Because we're saying here, we realize that there may be some possibility that you may incorrectly reject the null hypothesis, but we want to keep that to a minimum. So having something like 10%, so 10%, higher probability of committing a type 1 error. So in other words, a higher probability of me incorrectly rejecting the null hypothesis. That's a bad thing. 15%, that's worse. 20%, that's worse. So here you'll notice that as this number goes up, as the alpha level value goes up, the probability of committing a type 1 error, so in other words, the probability of me incorrectly rejecting the null hypothesis, here as that number goes up, that's bad for me. Because now there's a higher rate of me saying, hey, the difference between an 81 and an 80, that's a true difference, when in reality, there should be no difference between those numbers. Okay? And that's what I'm trying to avoid. I'm trying to avoid making this mistake of saying that there is a difference when in reality there is no difference. Okay? So what we do as researchers in the behavioral sciences, we keep this number low. 5%. That's a pretty conservative estimate, to be honest with you. That's a pretty conservative value here that we give, 5%. So that's a very low probability or percentage of committing a type 1 error. In other disciplines, for instance, in dentistry, if I'm not mistaken, alpha levels are sometimes given up to 7%. That researchers are allowed to go up to 7%. I've seen that in some journal articles. And for me as a behavioral science researcher, as a psychologist, I look at that and I go, wow, that's way too high. That's too high of a probability of committing a type 1 error. That's too high. My wife is a dentist, so her and I have statistical arguments from time to time, specifically about alpha level, that I say you put it at 5% or lower, and she goes, no, you can go all the way up to 7%, and I don't like it, and at the end of the day I'm right and I go to sleep happy, to be honest with you. In other disciplines they can go up to 10%. I believe, for instance, in medicine I've seen it go up to 10% in some particular cases. And why is it that certain disciplines go higher than others? Well, for other disciplines there may be a higher percentage of error that they're willing to accept and willing to live with. So in other words, for instance, if you look at the probability of committing a type 1 error in medicine, and you have a 10% chance that the medication that you just created in reality doesn't work, that's okay. For them, they're fine with that. For us in behavioral sciences, we're not okay with saying that there's a 6% chance, 7, 8, 9, 10% chance that we incorrectly rejected the null hypothesis. So in other words, we incorrectly are giving out this medication, telling people that it works when in reality it doesn't work. For us, that's too high. But for other disciplines, that's acceptable. So depending on your specific discipline, you're gonna realize that they're gonna have different alpha levels. For us in behavioral sciences, we set the maximum at 5%. This is max, okay? What's the minimum? Minimum alpha is whatever you want it to be. So you can go lower. You can go less than 5%. You want to go 4%? You can. 3, 2, 1%, half a percent, so 0.5%, 0.001%. You can do whatever it is that you want. But this has consequences. And this is very important. Doing this procedure here has consequences here that we want to try to avoid. So by decreasing the probability of committing a type 1 error, this will have consequences on your statistic. And we're going to talk about some of those consequences in just a couple of minutes here. Okay, so here alpha level, this is the probability of committing a type 1 error. Now, we also have this issue of a 1 versus a 2-tailed test. What is this issue of a 1 versus a 2-tailed test? If you look at this distribution, you'll notice here that we have a symmetrical distribution. So we have negative on one side, positive on one side, right? So this is negative, this is positive. So you'll notice here that since we have negative and we have positive sides, you have negative sides of the distribution or negative tails and a positive tail. Here, as a statistical researcher, you have the ability to decide if you want to look at only one tail, either the positive or the negative, or if you want to look at both tails of the distribution. Okay, now let's say, for instance, you want to look at one tail. So let's say that you're going to look at the positive side of the distribution. You absolutely can. You can do whatever it is that you want in whatever direction it is that you want. So here, I want to look at the positive side of the distribution. Here, that's perfectly fine. But one of the things that you have to consider is the following. Here, if you're looking at the positive side of the distribution, you're assuming that your stat's going to go to the positive side. So you're assuming in this particular case, for our example, that z would be positive. But what happens in the case where z takes a negative turn? So what happens in the case where z is negative? So you're looking over here, but in reality, you should have been looking over here. In a one-tailed test, your statistic, rather than being in this side, may have gone all the way over here. So it may have landed all the way over here. But here, it didn't land in here. So it didn't land in this side of the tail. So here, potentially, you're making a mistake, and we're going to talk about this mistake in just a couple of minutes here. So that's the issue with the one-tailed test. Now you're asking yourself, well, what happens in the case where we do have a one-tailed test? Can I move it over to the other side? You absolutely can. You can do whatever it is that you want. So if you were looking initially at the right side and you notice that your statistic goes negative and you want to move your tail over to the other side, that's where you want to look, you absolutely can look that way. Okay? You can definitely do that. But you have to do that after the fact. And we're going to talk about this issue of what we call a priori before the fact and post hoc after the fact. And we're going to talk about that issue in just a couple of minutes also. So here, rather than just looking at one side of the tail, we sometimes decide that we want to look at both sides of the distribution. So rather than just looking at one side, I want to look at both sides. Why? Because the two-tailed test functions like a safety net. So this is a safety net for us. Why is it a safety net? A two-tailed test functions like a safety net because just in case you think it's going to go to the positive side or go to the negative side, but it may go in the opposite direction of where you think it might go, you have a safety net that's going to catch it for you. Okay? That's a very important thing that we normally try to do. So here, what do we normally pick then? Do we pick a two-tailed or do we pick a one-tailed? It depends. You're going to notice that from here on out this semester, I'm going to start using this phrase. It depends. You're going to hate this phrase, but too bad. You're going to have to learn to love it, and you're going to have to learn how to use it too. And why? Because that's the truth. When it comes down to research and statistics, it depends on a lot of different things. And which one do you pick? It depends. Do you pick a two-tailed test? Well, it depends. Do you want to play it safe and have a safety net? Or do you want to really be, adventurous, right? I know that sounds weird, being adventurous in statistics, but do you want to be adventurous and a gambler here and go with the one-tailed test and only look on one side of the distribution? It depends. Why? Well, because it's going to have consequences. Having that safety net is going to have consequences. Not having that safety net is going to have consequences. Just like down here, looking at alpha level. So some of you may be saying to yourself, hey, 5% is still a lot for alpha level. Why don't we go down to 1%, giving ourselves a very small margin of error? You absolutely can. But again, it comes with consequences, and we're going to talk about those consequences in just a couple of minutes. So here, why or when would you want to pick this? Well, it depends. What does it depend on? It depends on what you think is going to happen. It's going to depend on your statistic. It's going to depend on a lot of different factors, and we're going to cover some of those factors in just a couple of minutes here. Okay, so in our particular case here, we've identified that we need these three key pieces of information: sample size, our alpha level that we select, and the one versus two-tailed design. Okay, so am I going to look at one side or both sides of the distribution? Now you'll notice here that this issue of one versus two-tailed only applies to distributions that are symmetrical and are normal. Okay, if they're not normal and symmetrical and don't allow for us to view both sides of the distribution, then there really is no debate. Some of our distributions that we're going to be working with, so for instance, our F distribution that we're going to look at this semester, I told you is positively skewed. So here, you don't even have to worry about this issue of one versus two tails because there is no other tail. So down here at the junction of the X and Y axis is 0. So here there is no negative side of the distribution. There's only positive sides of the distribution. So here we don't even have to worry about one versus two-tailed because you automatically always have a one-tailed here. But here with a normal distribution, you have that flexibility. So now you'll notice here, what are you in control of? You're in control of sample size, alpha level, and one versus two-tailed test. You're in control of all of that. You decided how many participants to have, You've decided what your alpha level is going to be. And again, here, remember, we want to have it set at the maximum of 5%. We never want to go higher than that. And you decided to look at one side or both sides of the distribution. Okay? Very, very important issues here that we have to consider. Okay, so now let's look at this issue of our critical value. So we've identified the 3 key pieces of information that are needed for identification of my critical value. Now here, if you're doing your own notes and following along with the lecture, which I am assuming everybody is, I would recommend having different color markers, different color pens or pencils, because I'm going to be drawing a lot of different colors here, and I want to make sure that you guys keep everything pretty consistent and organized for yourselves in this particular case. All right, so how do we find our critical value? So to find our critical value, again, I need my 3 key pieces of information here. So here, I'm just going to create my information here. So I know my sample size is equal to 25. My alpha level, I'm going to set it at the maximum because I'm allowed to set it at 5%. I'm going to set it at 5% or 0.05, right? And I'm going to say I'm going to look at a two-tailed test, okay? And why do I want to look at a two-tailed test? I'm a conservative kind of guy when it comes down to statistics. I like to play it safe, to be honest with you. So rather than playing it, too risky for me with a one-tailed test, since I don't know what direction my statistic might go in, I'd rather just do a two-tailed test in this particular case. Now, one of the things that we have to consider is the following. So when we do null hypothesis significance testing, right? So null hypothesis significance testing, we are doing one statistical test. So this equals one statistical test. Okay? If I were to calculate another group average, and I were to want to compare it to my population average of an 80, I would have to do another statistical test. I couldn't do 2 in 1, okay? Each time I calculate a statistical test, I have to do this process of null hypothesis significance testing. So every time I do null hypothesis significance testing, I have a specific sample size, a specific alpha level, and a specific number of tails, okay? Every single time I do my statistical test. So here, when we think about this aspect of an alpha level, the probability of us committing a type 1 error, so the probability of me incorrectly rejecting the null hypothesis. In other words, my statistic is not supposed to land in the region of rejection, and it does. So I want to avoid doing that. So the probability of me doing that error is at 5%. Now here, one of the things that you'll notice is that I have this option of a two-tailed test given to me, right? So I said I was wanting to do a two-tailed test, and since I want to do a two-tailed test, one of the things I have to consider is that every single region of rejection, right? So remember, my region of rejection, or my critical region that we also call it, is that area on a sampling distribution where I'm going to be able to reject the null hypothesis if my statistic lands within that region. So what I want to do is, on this distribution, I want to find my region of rejection. Alpha level corresponds directly to region of rejection. So how does it correspond directly to region of rejection? It corresponds in the following fashion. My region of rejection depends on alpha level. Why does it depend on alpha level? Because the region of rejection begins with the critical value. The critical value is identified depending on sample size, alpha level, and the number of tails. So ultimately, if my region of rejection is a two-tailed test, if my sampling distribution is a two-tailed test, so in other words, I want to look at both tails, region of rejection is singular. But since I have two tails that I want to look at, I now convert this region of rejection, singular, into regions of rejection. So in other words, I have regions of rejection, 2 of them. Now, like I mentioned, alpha level corresponds directly to regions of rejection because it corresponds directly to critical value. So now, since I'm going to have regions of rejection, 2 of them, because I have a two-tailed test, so in other words, I need to have a region of rejection on the positive side, and I need to have a region of rejection on the negative side. That's why it's my safety net, because I have one area on the top, right, on the positive, and one area on the lower end, the negative side. So here, since I'm going to have 2 regions of rejection, that means I need 2 critical values. Now, the good thing about my critical values and the regions of rejection for a normal distribution is, remember that when we were trying to find the probabilities in our previous homework assignments for z-scores, Remember that we said in a normal distribution, the beginning of your tail, so remember the beginning value for your tail was a 1.96 negative. You looked at 1.96, but it didn't have a positive or a negative sign. It just had 1.96, and then you would say, okay, it's negative or it's positive, right? So here, we're going to do the exact same thing. Once I identify my critical value, since it's a two-tailed test, I'm going to say it's a positive and also a negative. So my critical values are never going to be different from each other. So I'm never going to have one critical value that's going to be a positive 2.4 and a negative 1.96. I'm never going to have that happen. I'm always going to have positive and negative same absolute value. Okay, and that's very, very important for us to understand. And why? Because we're dealing with a symmetrical distribution. So here, since I have two critical values, two regions of rejection, because I have a two-tailed test, my alpha level is still set at a maximum of 5%. But now, since I have two tails and my alpha level is set at 5%, each tail gets half of that 5%. And this is the reason why. Let's assume here that I have 5% for every tail. So if I have one region of rejection set at 5%, and I have the second, so this is my first one, my second region of rejection also set at 5%, when I add those 5% up, what do I get? I get 10% total alpha level. That's too much, right? That's too much. I hate that. I'm sad now. I don't want that to happen. So rather, what do? I divide my alpha level in half that I've selected. So my alpha level of 5% has to remain intact. So here, what am I going to do? The first region of rejection is going to get 2.5% or 0.025. And my second region of rejection is also going to get 2.5% or 0.025. Now, if you're asking yourself, okay, can you give 3% to one tail and 2% to another tail? The answer is no. Why? Because again, we're dealing with a symmetrical distribution and we're trying to give equivalence to both sides of our distribution. We cannot give out different proportions to different tails in this particular instance. So we have to give out the exact same amount for every single tail. So we cannot give out 3%, 2%, 4%, 1%. Or anything like that, or 5%, 0%. If you're giving up 5% to one tail and 0% to another tail, you're doing a one-tail test. You're not doing a two-tail test in that instance. So here, we want to make sure that we give them equal amounts. So 2.5% and 2.5%. Okay, so now what do we need to find my critical value? So now I know it's a two-tail test. I know my alpha level. I know everything else that I need. What I now need to do for this particular example, okay, and this only relates to our example here for Z, okay? When we talk about the T statistic, R statistic, and F statistic, I'm going to show you guys different critical value tables. Here what we need is I need my unit normal table, okay? This unit normal table is used as my critical value table, so this becomes my critical value table for Z, okay? This is what this is in this particular case. So what I need to do now is I need to use this table here to identify my critical value. Okay, that's what I'm going to do. So here we've used it in the past to identify the probability that a statistic will land in that area, right? And the probability is X, Y, and Z. But now we're using this table to tell me what my critical value is. So here, what are we going to look at? To find my critical value, I need to look at column C. So I need column C. So the proportion in the tail. So here, essentially, the proportion in the tail for this particular table here is going to be equal to my alpha level that I've selected for a two-tailed test. Okay, and this is very important, okay, because when we look here on our distribution table, it's already going to assume that we're dealing with a two-tailed test and that it's already taken my alpha level and divided it by 2. So in other words, it's already selected my 0.05 and divided it by 2 to give me 0.025, or my 2.5% in this particular case. So here, when we look in column C for our specific proportion in the tail, so here we're looking for our alpha level. In this particular case, we are looking for an alpha level equal to 0.025, because remember, since it is a symmetrical distribution, it's going to identify for me one of my tails, so it's going to identify it for me at 0.025, and then since we're going to add in another tail, so we're going to assume this one's at 0.025, we're now going to assume this one's at 0.025. So I need my critical value for here and my critical value for here. So to find your critical value for each side of the distribution, we're going to scroll down until we find for proportion in the tail, because that's what we care about. Because remember, we're looking for the extreme ends of our distribution. Okay, so we want the point at where my region of rejection begins. So I want to know where my region of rejection begins. And then from that point on, everything is going to be considered my region of rejection. So in our particular case, we're going to look at what's called a proportion in the tail. So let's go and find 0.025. So 0.025 should be somewhere around, let's see, 0.025. Here it is. So proportion in the tail, 0.025. So now you'll notice that my critical value is this value of 1.96. So now here, remember, since it is 1.96, here I'm going to look at positive and also negative. Why am I going to look at positive and also negative? Because remember, I'm looking at both sides of the distribution. So in other words, when I go on here and I find in my table, I'm going to identify on my sampling distribution, my critical value equals 1.96 negative, and on this side, 1.96 positive. Okay, so all I've done here to identify my critical value for this particular example, for Z, the one that we're currently working with, I look at column C, which assumes that this is my alpha level for a two-tailed test, but it's already taken my selected alpha level and split my alpha level in half. So it's already taken my 0.05 and divided it by 2 because I have two tails. Now here, if you're wondering, well, can you have three tails? The answer is no, because this is not a three-dimensional distribution. We don't have another tail that goes north and another tail that goes south or something like that. We only have a tail that goes positive and a tail that goes negative in this particular case. So here it automatically divides it by 2. So when we look in column C, we're going to look at the proportion in the tail, and we're going to go down and we're going to find all the way until we find our selected value of 0.025. So remember, if we take 0.025 and multiply this times 2, that will give us our 5%, or 0.05. Okay, so don't make the mistake of going down and finding 0.05 or 0.05 in this particular case. We're not going to go do that. We're going to go and find 0.025 because that's representative of 0.025 for one tail and 0.025 for another tail. If you go here and you find 0.05, so here in our particular case, this is the closest that we have if we round off, right? So this would be 0.05. In reality, this is 0.05 for one tail, but if we're doing a two-tail test, this wouldn't really be a representative critical value, because that critical value there would represent 5% for one tail, 5% for another tail, thus giving you 10%. So here we automatically don't want to do that in that particular case. Okay, so when we go back here to our example, remember that our z-score that we had calculated in our study was a +3. So now we're going back all the way to what we had previously talked about, right, in terms of our presentation, that we had calculated a +3 for my example, right? So remember that my average that I calculated for my group was an 92. Population average was an 80. We divided it by the standard error, giving me a z-score of equal to 3. So now what I want to do is I want to compare where a value of a 3 lands. So I know that this is 1.96, okay? So now, remember, I told you that a critical value indicates for me the start of the region of rejection, or the critical region, okay? It starts the region of rejection. So in other words, 1.96 begins the region of rejection. Everything to this side, of 1.96 and everything to this side of 1.96 is going to be region of rejection. So this is my region of rejection and this is my region of rejection. Okay. Why do I have two? Because I selected to have two regions of rejection in our particular case. So again, the 1.96 in this particular case, this critical value, indicates for me the beginning of my region of rejection. So if you look on page 247 of your textbook, you'll notice there that we have negative and positive 1.96 being represented for alpha level 0.05. So why is it for 0.05? Because remember, for one tail, we gave it 5%, or we gave it 2.5%. For another tail, we gave it 2.5%. Okay? So in this particular case, we now want to identify where my z-score of a 3 occurs. So here I'm going to just change the color very quickly of my marker so that way we can identify where this value is going to occur. So we're going to find where a positive 3 occurs. Positive 3 should be somewhere around here. Okay, this is where I'm going to draw it. Okay, so that's where positive 3 falls. How do I know that's where positive 3 falls? And here I just arbitrarily put it into that area because I know a positive 3 is larger than a 1.96. So here, a positive 3 lands inside of this region. So here now, what am I going to do? So now my statistic has landed inside the region of rejection. So now I've set all my characteristics appropriately. I have my sample size appropriate at 25. My alpha level has not exceeded 5%. I have a two-tailed test. I'm good. So here you'll notice now that since my z-score of a positive 3 has landed in the region of rejection, now what do I do about the null hypothesis? And here, if you're wondering, okay, well, we identified if my statistic landed in the region of rejection, what's the fourth step then in null hypothesis significance testing? The fourth step in null hypothesis significance testing is making a decision regarding the null and alternative hypotheses. Now here, I'm going to go back to this issue here of calculating the p-value in just a second here, because that is an important issue that we have to talk about. But here I just do want to present for you the decision step in terms of null hypothesis significance testing. And in this particular case, my decision is, since my statistic landed in the region of rejection, I can reject the null hypothesis. So it is rejected. So since I've rejected the null hypothesis, what does that mean for the alternative hypothesis? This is accepted. So why have I done this? Well, because remember, my statistic that I calculated for my study was equal to a positive 3. My critical value, using these characteristics of an alpha level at 5%, a two-tailed test with a sample size of 25, provided me with a critical value of 1.96 positive, 1.96 negative. Remember, it's giving me a positive and a negative because I'm looking at a two-tailed test. This side gets 2.5%, this side gets 2.5% to never exceed the 5% total, right? So down here, I'm still at 5%. My z-score of positive 3 lands inside of this area right here. So it lands inside of the region of rejection, thus I can reject the null hypothesis. And since I've rejected the null hypothesis, by default here I'm saying I've accepted what the alternative indicates. So if I'm rejecting what the null hypothesis says, what does that mean? So if I reject the null, I'm rejecting the statement that there was no difference between my sample mean and my population mean for our given experiment. That's the statement that I'm rejecting. So since I'm rejecting that statement saying that there was no difference, then what am I saying? I'm saying that there is a difference between them. I'm saying that there is a difference here between 92 and an 80 in our particular study. So in other words, in our particular example that's given to us in the chapter for 8.1, the conclusion then that we're drawing is that using some type of intervention technique here, and in this particular case, if I'm not mistaken, it was giving individuals a particular type of strategy, a strategy that was given to them so that way they can perform better. Using that strategy apparently does help them perform better than individuals who are not given that strategy. Because individuals who were not given that strategy gave us a population average equal to an 80. Once we give individuals that strategy, they now give us a sample mean of 92. That difference is extreme. That difference is now significant. Now, does this mean it's an important finding? No, it doesn't mean that at all. Because remember, significant does not mean important. Significant, all that it means for us is that we found extreme differences or extreme relationships in our data. So in our particular case here, we have now identified that our z-score of positive 3 does land in the region of rejection. I've rejected the statement that there is no difference between my sample mean and my population mean in terms of assessments that were given to individuals, the performance assessments. So I accept the alternative hypothesis indicating that there is a difference between my sample mean and my population mean in this particular case. For this particular example, when we cover t statistics, we're going to modify our statements to correspond to t in those particular cases. Okay, so now here I've given you the example where we've done a two-tail test. Now what happens in the case where we do a one-tail test? So let's say, for instance, my z-score was not a positive 3. Let's say my z-score was a negative 3. Okay, and that's just an example that I'm coming up with. So if you're wondering where I came up with negative 3, I'm just coming up with it as just to show you an alternative to a positive 3. But now let's say that we're doing, oops, that's a terrible distribution. Still terrible. A little bit better. You guys get the idea, right? I won't spend too much time trying to make a perfect distribution. Okay, so here I have a 0 for my normal distribution where the null hypothesis is true for z. And in this particular case now, I'm going to just change around some of these characteristics. So my sample size is going to remain the same, 25. Alpha level is going to be at 5%. And I'm going to go one-tail test, right? So now we're just changing this around. So it's a one-tail test. So in this particular case, what I now want to do is I want to look at my unit normal table and I want to find on here for a one-tail test. So remember I told you that here column C automatically is assuming that we have an alpha level here and that it would automatically cut it in half if we were doing a two-tail test. But now I've changed around my characteristic. So now column C represents, there we go, alpha level for a one-tail test. Okay, why does it change now? Because I've changed the characteristics. Okay, that's the only thing that's done here, that I've changed the characteristics. So now here, column C is going to look for an alpha level that I've specified for a one-tail test. So here it's not assuming that it's going to divide it into 2. It's going to assume it's equal to whatever I set it at. So here it's going to assume that it's equal to 0.05 because that's what I've stipulated alpha level to be at. So what I'm going to do is I'm going to go down to proportion in the tail and I'm going to find 5% or 0.05. So it's right here, right? It's the one that we had circled before. So in this particular case, I now am identifying that I have a 5% alpha level, and this is my critical value for that one single tail. This is okay for me to look at this now because I'm not assuming that there is another tail. I'm only assuming that there is one single tail here. So now that I'm looking at this one single tail, I've identified that my critical value should be equal to a 1.65. But now here, let's make the decision. What side of the distribution are you going to look at? Positive or negative? Now here, I've already told you that my z-score is a negative 3, but you don't know this. Okay, you really don't know that information before you do the statistical test. You don't know what your stat is. So here, if you set a one-tail test, I'm going to say here, being the statistician that I am, that I'm going to look at the positive side of the distribution. So I'm going to set it right here. So my critical value is equal to a positive 1.65. Now, if you're wondering, why does your critical value change from a 1.96 in this example to a 1.65 here? Remember, here I was doing a two-tailed test, so my alpha level was split in half. Here I'm doing a one-tailed test, so this entire region of rejection gets all 5%. I don't have to give it 2.5% because there is no other tail that I'm looking at. Okay, that's why the critical value gets lower. So you'll notice now that as alpha level goes up, my critical value gets closer, there we go, to 0, and my region of rejection gets larger. Okay? So again, as alpha level goes up, my critical value gets closer to 0, and my region of rejection goes up. So in other words, it gets larger. Okay? That's what I'm talking about here. It gets larger in this particular case. Now, why does this happen? Well, again, remember, here in this particular case, alpha level is having to be split into two. So this side is getting 2.5%, this side is getting 2.5%. Now we're saying that alpha level is all 5% on this side. So we have a higher alpha level on this side of the distribution. Thus, I have an alpha level that is greater. My critical value, now if you notice, gets smaller and closer to 0. Here, it got larger and farther away from 0. And my region of rejection also gets larger. Why does my region of rejection get larger? Because my critical value gets closer to 0 in this particular case. So for this occurrence now, we now say my z-score equaled -3. Okay? So you didn't know that it was going to be a -3. You just said you're wanting to look at the positive side of the distribution for a sample size of 25 and alpha level at 5%. Your critical value was 1.65 in that particular case. So now we have to go find -3. So here, let me just change colors one more time. Here now, I'll go in red. So now I go and find -3, and I find that -3 is right here. So this is my z-score equal to -3. So now you'll notice here that you say, oh wow, so my -3 is a very large number, but where's your region of rejection? Your region of rejection is over here, because remember, the critical value begins the region of rejection. This is not the region of rejection. This is the area where we're going to retain the null hypothesis, because remember, the critical region begins the region of rejection. So that value and greater is going to be my region of rejection. So in this particular case, it's all of this area in the tail, that proportion in the tail. So now you'll notice here, my z-score of -3 goes all the way over here. You'll notice now, if I was looking in the right direction, so if I was actually looking here for this side, so rather than being positive, I was looking at negative, I would have been okay, right? My statistic would have landed in my region of rejection, but I wasn't. I was looking at the positive side of the distribution. I was looking over here. So I'm wrong. So in this particular case here, what do? Does my stat land inside or outside the region of rejection? It lands outside. So this is outside region of rejection. Should it have landed inside? Yes, it should have landed inside. So here, going back to our definitions of our errors, what kind of error am I making? Am I making a type 1 error where I've incorrectly rejected the null hypothesis? Or am I making a type 2 error where I've incorrectly retained the null hypothesis? And the answer is, I've made a type 2 error. So in other words, I should have rejected the null hypothesis because my statistic should have landed in the region of rejection, right? So here, this value should have landed here, right? If I would have been looking on the right side of the distribution. So I should have had that happen, but I didn't have that happen. Rather, what occurred? Well, I was looking at this side of the distribution over here, and my statistic landed over here. So what happened? I made a type 2 error. So in other words, my statistic should have landed inside the region of rejection, but it didn't because I was looking on the wrong side of the distribution. Now, can I remedy this situation? And the answer is yes. How do I remedy it? Let's go back, redo our statistical analysis. And rather than looking at the positive side of the distribution, we're going to look at the negative side of the distribution. And now my critical value becomes a negative 1.65 rather than a positive 1.65. So we delete all of that, and now this becomes my region of rejection. So now, in this particular case, does my statistic land inside or outside the region of rejection? It lands inside the region of rejection. Right? So here, I've now rejected the null hypothesis. Sorry, reject the null hypothesis. So you're asking yourself probably this question: is that fair? Does that sound ethical to actually do that? And the answer is actually yes. You can definitely do that. This brings us to a very important junction in terms of learning statistics. This is what we're going to talk about: a priori. So a priori, or what we call post hoc test. A priori means before the fact. Post hoc means after the fact. Okay, so how does this remedy the situation that we just encountered? So in this particular case, we looked in the wrong direction. So in one case, we retained the null hypothesis and we were supposed to reject it. So I've made a type 2 error. But now I've gone back, looked at the right side of the distribution, so looked at the negative side, in this particular case, the left side, and now I've rejected the null hypothesis. Does that decrease the validity of my results in any capacity? And the answer is no. It does not decrease the validity of your results in any capacity because you haven't changed your numbers in any way. All that you've changed is where you're looking at to see where your statistic landed. So your z-score has not changed. It's still a -3. The only thing that changed is the sign of your critical value from positive to negative, and that's okay. Now, all that you have to do is you have to do the following. Admit to what you did. A lot of people don't do this. A lot of people just say, no, 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 no. You know, I totally knew it was going to go to the negative side. That's why I looked there. Or I totally knew it was going to go to the positive side. That's why I looked there. So a priori, if you say, look, I looked at the positive side, it didn't go there. But then I did it again, post hoc, after the fact, after knowing what my statistic was, I looked at the negative side and I rejected my null hypothesis. So I rejected the null. People are going to look at that and be like, okay, that's fine. But if you don't admit to that, that's where we have a problem with ethics. That now you're technically lying to people and you're telling people that, hey, I knew it was going to go in that direction and that's why I looked there. This is why, again, we normally try to go with a two-tailed test. We rather play it safe. That we rather say, I'm going to look at both sides of the distribution rather than only one side of the distribution. Why? Just in case. Just in case things go sour and in the opposite direction of where I predicted, I can still find my result. Now, another important issue that we have to talk about, the aspect of alpha level. Okay, so let's look at alpha level again. So if you notice here, I'm drawing lots of distributions. My drawing skills have gotten down a little bit, to be honest with you. I'm sorry, I think it's just fatigue that comes into play with the drawing process. Let's now assume that everything else remains constant. Sample size is at 25. Alpha level, now we go from a 5% to a 1%. Okay, 1%. And we're going to do a one-tailed test just because it shows the exact same thing as with a two-tailed test, because the same thing will kind of happen in this particular case. So I'll show you a two-tailed example in just a second as well. But here with the one-tailed test, so what we now need to do is we need to go and find 1% or 0.01 in column C. Okay, so in column C for our critical value table. Okay, so we're going to go back to our critical value table and we're going to go find 0.01. So 0.01, or the closest that we get to 0.01, which should be this value right here. So 0.01, it's that value right there. So we have 0.01, and that gives me a critical value of 2.33. Okay, so 2.33. So here, let's look at this example. So when we set up with an alpha level of 0.05 or 5%, my critical value was 1.65, right? So we're going to just put it here on the positive side of the distribution. Okay, positive 1.65. I'm going to draw that in red. Okay, so now I'm going to, in blue, draw alpha level 0.01 or 1%. Because remember, we had asked this question at the beginning that we said, okay, you can go down lower than 5%. You want to go 4%, 3%, 2%, 1%, 0.5%, 0.001%. You can do whatever you want, but there are consequences to doing this, right? That's the thing that I indicated here. There are consequences to doing that process. Why would a researcher want to go lower in alpha level? Well, the lower your alpha level, the lower the probability of incorrectly rejecting the null hypothesis, right? That's a good thing. So the lower the probability of me making an error, that's good. So I'm not going to incorrectly reject the null hypothesis. That's a good thing. So now here we scroll down and we say, okay, well, what's the difference then in terms of 0.05 and 1%? So for 0.05 or 5%, our critical value was a 1.65. For 1%, my critical value now is 2.33. So positive 2.33. So positive 2.33. So now you'll notice as alpha level goes down, what happens to my critical value? Does it get smaller or larger? So does it get closer to 0 or further away from 0? And the answer is it gets further away from 0. So it starts getting larger, right? So the absolute value becomes larger. So it starts getting further away from 0. What happens to my region of rejection? Does it get larger or smaller? So look at the proportion in the tail. Does it get larger or smaller? So we have 5% here. Now we have 1% here. So this goes down. So as alpha level goes up, or sorry, yes, as alpha level goes down, there we go, sorry. As alpha level goes down from 5% to 1%, critical value gets farther away from 0, the region of rejection gets smaller. Why is this important? Why does this matter? So if you're looking at this and you're like, all right, that's great, go back to sipping my coffee or my tea, what does this matter at all? Remember, I told you that you set alpha level before the fact. You set this before anything happens. So since you're setting this before anything happens, you don't know what your statistic is. So what happens in the case where your statistic is a value equal to a value of a 2? At 5%, you're going to reject the null. Why? Because at 5%, your z-score of a 2, and I'm going to put this in green for us to see where our z-score would land. Our z-score of a 2 would land somewhere just about here. Our z-score would land just about there. So at 5% with a critical value of 1.65, I rejected the null hypothesis. But now you'll notice with an alpha level at 1%, what happened to my statistic? Did it land inside or outside the region of rejection when my critical value was 2.33? So 1% alpha level. I've now retained the null hypothesis here. So in one instance, I rejected. In another instance, I retained. So now what do? Can you go back and modify and say, okay, well, oh no, look at that, At 1%, my statistic lands just outside the region of rejection. Oh no. Well, can I go back and change it to a 5%? And the answer is, yes, you can. What do you have to do? Go back up to this issue of a priori and post hoc. So in other words, all you have to do is admit to what you did. So in other words, you can say, look, we initially set up our alpha level at 1%. Our critical value was 2.33. My value that I calculated from my statistic landed just outside the region of rejection, potentially indicating that I've committed a type 2 error. So in other words, I should have rejected the null hypothesis, but I didn't. So I failed to reject the null. So what can I do now? Well, I've gone back, redone my statistical test, given myself an alpha level of 5%. My critical value now becomes 1.65. Now my statistic lands inside the region of rejection, and I've rejected the null hypothesis. I'm okay. And that's not a problem, because here you've admitted to it. And that's ultimately what we want about statistics, that you demonstrate to us what it is that you've actually done in this particular case. So here now I've shown you what happens in the case of a two-tailed test, a one-tailed test, decreasing and increasing alpha level. So you'll notice now that when I went from a two-tailed test to a one-tailed test, my region of rejection got larger. So when I went from a 2 to a 1, okay? So a two-tailed test leads to smaller regions of rejection. It leads to larger critical values. And why? Because my alpha level has decreased per tail. So in other words, rather than me having 5% for one tail and 5% for another tail, I have, in this particular case up here, 2.5% and 2.5%. It's essentially the same thing as me having done what I did here, that I went from 5% to 1%. I went to a smaller alpha level per tail. So now here I went from a 5% to a 1%. Well, of course, it's going to make my critical value go up, my region of rejection smaller, because my alpha level has decreased in that particular case, because it's decreased per tail for a two-tailed test. Okay, very, very important. So we see here the effect of our tails as being a very integral part to this idea of, will I reject or will I retain the null hypothesis? Because ultimately, that's the goal. Do I retain or do I reject the null hypothesis? That's what I want to try to decide on. Okay. Now, a very important point here, and let me just get rid of all my scribbles. So again, just to reiterate the situation that we encountered in terms of the issue with a one-tailed versus a two-tailed test, again, you'll notice that in this particular example here in figure 8.6 that's located in your textbook, you'll notice here what happens whenever it is that we decrease our alpha level from one specific value to a lower value. So again, indicating for us that as we decrease our alpha level, which is a good thing, right? So we do want to, in certain instances, decrease our alpha level, but for practical purposes, we probably would not want to do that. So in terms of decreasing our alpha level, when is it that we would actually want to decrease an alpha level? We would want to decrease an alpha level if we want to become more confident that our effect is actually due to my manipulation or to my control. So when I decrease alpha level, what is that essentially saying? That if I end up rejecting the null hypothesis, so if I reject the null hypothesis, even with a very, very low alpha level, I'm going to be very confident. So my confidence increases associated with the differences between my scores being due to my manipulation or my control. In other words, effect variance. So if you remember, we've talked about this issue of effect versus error variance numerous times this semester. And again, here we're encountering the same situation. That here we're now saying, look, if we find that they're still rejecting the null hypothesis, even if I decrease my alpha level from 5% to 1%, to 0.001%. And if you do notice here we're talking about two-tailed test, but here the same thing happens for our one-tailed test. So don't necessarily think that this only applies to two-tailed test. It also applies to one-tailed test. So if at a two-tailed test or at a one-tailed test, I decrease my alpha level from 5% to 1% to 0.001%, or sorry, from 5% to 1% to 0.1% in this particular instance, I would then become much more confident that the differences between, in this case, my average and my population average, so mu, so my sample mean minus my population mean, if I do find that there are differences between those two groups, at a very, very low alpha level, I'm going to become very confident that those differences are actually due to my manipulation and my control and not just due to random chance. So in conjunction with this issue of random chance, we have to think about this issue about probabilities again and thinking about why probabilities are so important. So in one of our previous slides in terms of the steps associated with hypothesis testing, I put on there one of the bullet points was looking at the p-value and deciding if your p-value was less than or greater than 0.05. And this aspect of a p-value is very, very important for us in statistical testing. Many times what you're going to find is that you're going to find in research articles something that's called your p-stat. So many times what you're going to find is you're going to find something that looks like the following. Z is equal to positive 3 and then it's going to say p less than 0.05, or it's going to say p greater than 0.05 associated with your statistic. You're going to find that very, very frequently in terms of your research articles. Now, what is this in reference to? So your p statistic, again, going back to our discussion of probability, your p statistic is actually the statistic that is used for us to determine what the probability that my statistic that I've calculated was due to chance. So in other words, what is the probability that my statistic of a positive 3 was solely due to chance? So ultimately, we want to determine, was the probability that my statistic of a positive 3, was it greater than 5% or was it less than 5%? Now you will notice that here I again am talking about 5% or 0.05, but never get p-value and alpha level confused. They are not the same thing. Alpha level, again, is the probability of us committing a type 1 error. That applies to null hypothesis significance testing. P-value is the probability that my statistic, the one that I've calculated for my study, occurred solely due to chance. In other words, because of random error variance or because of random sampling error, we now have this value here as a representation of the differences between my scores, but in reality, it's due to error or it's due to chance. So here, p-value is the probability that the statistic that you calculated, that you found, was due to chance. That is not the same thing as alpha level, so do not get those two confused. It can be very confusing because of the 0.05 or the 5% rule, but they are very, very different. So let's set up a situation. In a situation, for instance, you may look at something like the following. Looking at the differences between psychology and kinesiology majors on their GPAs. And one of the things that we may do is we may look at the differences between those two z-scores. So we may look at the difference between the z-score for psychology majors and the z-score, or for instance, creating a z-score looking at the difference between psychology majors and kinesiology majors. So let's say, for instance, I calculate the average for my psychology majors, and that's a value of a 3.4. And what I also do is I know what the population average is for kinesiology majors, so I want to compare my value to the value of kinesiology majors, and in this particular case it's a value of a 2.1. Again, my null hypothesis would predict that both averages would be identical to each other, but here I want to see if there's a difference between the two. So here I look at the difference between those scores, and what I'll identify is that my z-score, for instance, let's also say it's a p of positive 3, and that's just one that I'm just creating in this particular instance. So associated with this statistic that I've calculated, I now calculate a p-value. This p-value is going to determine for me if my statistic occurred solely due to chance or not. So the rule of thumb that we use is we use the following rule. If my p-value is equal to or greater than 0.05, so this is my equal or greater sign, right? So greater than or equal to 0.05, we retain the null hypothesis. If p-value is less than 0.05, we are going to reject, oops. So we're going to reject the null hypothesis. So if my p-value is less than 0.05, I'm going to reject my null hypothesis. If my p-value is greater than 0.05 or equal to it, I'm going to retain my null hypothesis. Now, as a standard, we always use these statements. So if p-value is less than 0.05, we are going to allow you to determine that the differences between, in this particular case, your mean and your population average are significant. So in other words, there was a difference, there was a relationship. Or in this particular case, that we're going to reject the null hypothesis, and we're going to assume here that your stat was in region of rejection. Okay, that's what we're going to assume here, that your statistic was in the region of rejection. So if your p-value is less than 0.05, we're going to assume that your statistic was in the region of rejection. That's why you've rejected the null hypothesis. So when we think about this aspect of the p-value corresponds to this idea of where your statistic lands in the region of rejection or not. So in the case where we have a value such as here, so for instance, when we had our alpha level at 0.05 or at 5%, and my statistic was right outside the region of rejection, so it's right there. So it lands right out, when my alpha level was 0.05%, my p-value lands right inside the region of rejection. So my region of rejection begins right here with this critical value of 1.65. My statistic lands inside the region of rejection. I'm now going to assume that p was less than 0.05. Why? Because p-value corresponding to less than 0.05 suggests that your statistic landed in the region of rejection and you're able to reject the null hypothesis. But in this given occurrence, that your p-value or that your alpha level was 1%, your critical value becomes 2.33%, and your statistic lands just outside the region of rejection, so it lands on the left side of this blue line. In this particular case now, let me see if I can draw that. Okay, no. Okay, there we go. In this case, my p-value is going to be greater than 0.05 or equal to it. Okay, and why? Because it corresponds that if p is equal to or greater than 0.05, we are going to retain the null hypothesis. So here, one of the things that you're going to find very interesting about statistical testing is the following. That if we have a sampling distribution that looks like the following, right? So here's my zero value, and here's my critical value, right? I'm just going to identify my critical value there. The further along that my statistic falls inside the region of rejection, the lower the p-value. So here, p may be equal to 0.04. This is going to be equal to 0.03, 0.02, 0.1, etc., etc., etc. So the further that your statistic that you calculated, so in our particular case, the z-score that we've calculated for this particular example, the further it goes into your region of rejection, that means the larger your statistic and the lower your p-value. Why the lower the p-value? Because it's a lower probability that your statistic is occurring due to chance. So the likelihood that your statistic landed that far into the region of rejection is due to chance, it seems very, very unlikely. So in reality here, what would we want? We want our statistic to land into the region of rejection. If it's supposed to, and that's a very important statement there, we want your statistic to land in the region of rejection if it's supposed to. I don't want to commit a type 1 error. So I want my statistic to land in of rejection because it's supposed to land in the region of rejection, not because of something that I've done to make it land in the region of rejection when in reality it's not supposed to. So in other words, are there ways that I can make my statistic land in the region of rejection when it's not really supposed to land in the region of rejection? And the answer is yes, you can absolutely do that. You can manipulate your numbers to make your statistic land in the region of rejection when in reality it should not. So in our particular case here, the further along that your statistic lands inside of the region of rejection, the lower your p-value will be. So think of it in the following form, that if my z-score equaling to a +3 lands inside the region of rejection, p-value may be equal to 0.01. If z was equal to a +4, p-value may be 0.008, so a smaller p-value. If z was equal to a +10, I don't know, let's say, right? P-value would then be maybe equal to 0.000001 or something along those lines. Okay, so here, these numbers I just came up with here, but just to kind of show you how our p-value would decrease. So in other words, the larger that my statistic is, the further along into the region of rejection that it actually occurs, the lower my p-value will be. Okay, the smaller my statistic, the larger my p-value. So z equals positive 2. So positive 2 may have a p-value of 0.04, so it's still less than 0.05, but z equal to a 1 may have a p-value equal to 0.05. Okay, so you'll notice that my p-value now starts getting larger. Z is equal to 0.2. So very, very small z-score. P-value is now equal to 0.8, for instance. So a very large p-value. So here, my point is the following. So the larger my statistic is, the further into the region of rejection it will be, the smaller your p-value will be. So the smaller the probability that this number occurred solely due to chance. So the likelihood that this number is occurring just due to chance seems very, very unlikely according to my p-statistic. Okay? Now, your p-statistic is going to depend on your critical value and how far into the region of rejection your statistic lands in that region of rejection, thus corresponding to the p-value that will be given for it. So in other words, we would then go back to our unit normal table and say, okay, what is the probability that any statistic will be larger than this? And then that would determine your p-value for you. But in our particular case, if your z-score does not land into the region of rejection, a p-value will still be associated with it. So just as in the case here with a 0.2 or a 1, that these numbers no longer land into the region of rejection. So here your p-value will correspond to you retaining the null hypothesis. So here, if your z-score in this particular case or your stat lands in the region of rejection, and it's supposed to land in the region of rejection, your p-value will also identify for you that you should be able to reject the null hypothesis. So if on an example, for instance on the exam, I were to say to you, z equals positive 2 and a p-value less than 0.05, how would you interpret that? You would essentially say, well, your z-score falls inside the region of rejection, thus allowing you to conclude that the null hypothesis is false. So here, I didn't even need my sampling distribution. I didn't need anything. I don't need to do this whole thing that we were just talking about doing in terms of finding your critical value or anything like that. You can use just this p-value to determine if you should reject or retain the null hypothesis. That's a very, very common practice that we use in statistical testing for the behavioral sciences, especially in psychology. All right, so again, remember that your p-value is the probability that your statistic is due to chance. We consider extreme statistics to be significant. Again, remember that the term significant does not mean important. What do we mean by extreme statistics? We mean the statistics that land in the region of rejection and have p-values less than 0.05. Significant for us in statistical testing means it's a large or extreme enough for us to interpret and to draw conclusions that there are differences between the numbers. Between what numbers? Between my calculated statistics, between my calculated statistic and the zero value given to me by the null hypothesis. So thus, if we ever do find the situation where we were to reject the null hypothesis and conclude then that your statistic was large enough for us to interpret and to determine that it is different from, for instance, in this case, our population mean, that would lead us to believe that that statistic or that sample is being produced by a different population other than the one that the null hypothesis predicted. So in other words, let me just add in here another page very quickly. So in other words, think of the following situation. Let's say here that we're going to draw, again, our distribution. And here I'll do it in blue just so it can be a little bit darker here for us to see. So I draw my distribution. I have my zero value. I identified my critical value, and again, in our case, let's just say it's a 1.65 positive, right? Whatever the value is. And we find a statistic that lands inside of the region of rejection. So we have a value that lands in here, right? So now what does this mean for me? This essentially means the following, that initially we assumed that in this particular case, the one that we're working with for z, we assumed that the z equaling 0 would represent the population average equal to an 80, as in the case of the book, right? The example that's given to us in the book. So now for our purposes, we find that our z-score, or that our average is not an 80, but rather it is a 92. So the difference between my mean and the population mean of 80 was a z-score of a 3, right? So it's a z equaling a value of a 3 in our particular case. So thus, it's that value that's right there. So this would suggest for me then that if I were to find this result where I reject the null hypothesis, so in other words, that the difference between my sample mean and the population mean would be equal to 0, so in other words, my sample mean would be equal to an 80, thus giving me the difference of 0, if I were to find that this happens where I reject the null hypothesis, right, so I reject the null hypothesis, then I'm assuming the following. I'm assuming that I have a different distribution where this is the average. Okay? That's what I'm assuming here. That's what I mean by this statement here, leading us to believe that the statistic may have been produced by a different population than that of the null distribution. Because the null distribution assumed that my statistic should have landed right here. That's what my distribution assumes, that my statistic should have landed right here. But it didn't land right there. It landed all the way over here where I rejected the null hypothesis. So what do I do in this particular case? I'm going to assume then that this number here is coming from a different population than that where the null is true. So in other words, this number here, the sample that I've calculated where they got a value of a 92, because remember my average was a value of a 92, for them, they come from a different population than that where an 80 should be produced. Okay, that's what we're referring to in this particular case. So in our particular case, if we have a stat that lands in the region of rejection, we're going to assume then that my distribution is going to look like the following, that we're going to have a distribution that comes from a different population other than the one where the null hypothesis is true. So in other words, this is the distribution where the alternative hypothesis is true. That's what we would assume in that particular case. All right? Very, very important for us to consider those issues. So when we think about the decision-making process associated with statistical testing, we have to consider the following. If my statistic that I've calculated is less than the critical value, then there is no effect. So my statistic does not land in the region of rejection. Now, if my statistic is greater than the critical value, then we're going to assume that there is an effect, that my statistic falls in the region of rejection. Now, very important, if my statistic is greater than the critical value, and I'm concluding that there is an effect, in other words, that the null is false, and my statistic lands in the region of rejection, when my statistic lands in the region of rejection, and it's supposed to land in the region of rejection, I found what is called power. A very, very important term for us. What is power? Power is defined as the probability of correctly rejecting the null hypothesis. So I'll say that again. Power is the probability of correctly rejecting the null hypothesis. In other words, we are saying my statistic was supposed to land in the region of rejection. My statistic has landed inside the region of rejection. So in other words, I've correctly rejected the null hypothesis. The way your textbook defines power on page 265 is the following. The power of a statistical test is the probability that the test will correctly reject a false null hypothesis. To put that in simple terms, power is the probability of correctly rejecting a null hypothesis. That's what that means for us. Correctly rejecting the null. So in other words, my statistic was supposed to land in the region of rejection. My statistic has landed in the region of rejection. I found power. I have that correct. Now, in the case where my statistic lands in the region of rejection and it wasn't supposed to land in the region of rejection, that's what we call our type 1 error. Right? And that's what we want to try to avoid. We want to try to avoid type 1. We want to try to avoid type 2 error. Okay, why do we want to avoid those? Because those are both mistakes and we're drawing incorrect conclusions. So here, what happens in the case where my statistic does not land in the region of rejection and it wasn't supposed to land in the region of rejection? So in other words, the statistic does not fall in the region of rejection and it really wasn't supposed to land in the region of rejection anyways. So what happens there? Nothing. You're okay. You supported the null hypothesis. You're perfectly fine. So in that instance, you support the null hypothesis. Okay? Now, this means for us that we have to consider some very important contingencies. So when we think about decision making associated with null hypothesis significance testing, there's really two possibilities. Either you reject the null hypothesis and you accept the alternative, or you retain the null hypothesis. Those are your options. Those are the two decisions that you can make. So that's step 4 for us in null hypothesis significance testing. Either you reject or you retain the null hypothesis. That is it. There's nothing else that you can do. You either reject it or you retain the null hypothesis. Now, there are some very important contingencies that we have to think about in terms of null hypothesis significance testing. Because if two possible contingencies exist, if an effect does not truly exist in nature. So in other words, in reality, the null hypothesis is supposed to be true. Okay? So here, one option here, or one possible result that may happen in null hypothesis significance testing is the following: that you find a false effect. In other words, if in reality the null hypothesis is supposed to be true, yet you rejected the null hypothesis. So in other words, your statistic was not supposed to fall in the region of rejection, yet you're claiming that it did fall in the region of rejection and it wasn't supposed to. So you've incorrectly rejected the null. This is what we call our type 1 error. Contingency number 2 is that if the null hypothesis is true and you correctly identify that there is no effect, in other words, your statistic lands outside the region of rejection, it falls short of the critical value, then you've retained the null hypothesis correctly. Those are your two possible contingencies if an effect does not truly exist in nature. Now, with the same issue, two possible contingencies occur if an effect does truly exist in nature. In other words, if in the real world the null hypothesis is supposed to be false, there's two possible results that may occur for us. Number 1, you miss a true effect. In other words, you were supposed to reject the null hypothesis, but yet you retained the null hypothesis incorrectly. Thus, you've committed a type 2 error. Do not get type 1 and type 2 confused. Very, very different. Remember, with type 2, you're incorrectly rejecting the null hypothesis. With type 2, you're incorrectly retaining the null hypothesis. Okay? What's the second possible result that we may have? We have power, where we have a true effect. In other words, I correctly rejected the null hypothesis. So remember that with power is the probability of us correctly rejecting the null hypothesis. In other words, us correctly saying that there is a difference between my values when in reality there was a difference between your values. So we can also think of these contingencies in the following square diagram here that I've placed for you. Now, if at the top you notice here, this is the reality of the situation. Okay, this is the true world, this is reality. So this is the population, if you want to think about that, right? So remember that I said that in inferential statistics infer about the population. What do they infer about the population? They infer about the null and the alternative hypothesis, okay? The null hypothesis and the alternative hypothesis. Those are my two options there. So in reality, in the population, those are the two possible results that may exist. My conclusions, based on my research, are the following. I either retain the null or I reject the null. So you'll notice here that both retain the null and reject the null are represented right here. The null being true, you retain the null. The null being false, you reject the null. So in other words, in reality, I'm either saying that the null is true or that the null is false. In my research, I'm either saying that the null is true or the null is false, depending on what I find. So let's begin here thinking about the possible combinations. Let's begin first here. If in reality the null is true, so out there in the real world, there is no difference between your groups. There's no difference between your mean and the sample. There's no difference between your sample mean and the population mean. In your research study, you concluded that there is no difference between those two numbers. So out in the real world, there's no difference between those numbers. You concluded that there is no difference between those numbers. You're okay. If out in the real world, the null is false, yet you've concluded that the null is true. So in other words, out there in the real world, there is a difference between your sample mean and the population mean. Yet you concluded that there is no difference. What do we have there? We have type 2 error. So in other words, out there in the real world, there's supposed to be a difference, yet you concluded that there was no difference. So you've incorrectly retained the null hypothesis. That's a problem for us. Now, out there in the real world, the null is true. No differences between the groups. You say that there are differences between the groups. So there are differences between those numbers. You've made a type 1 error. So in other words, out there in the real world, groups are not supposed to be different. You're supposed to retain the null hypothesis. In your research study, you've rejected the null hypothesis. You've committed a type 1 error. Now last, out there in the real world, the null is false. In your research study, you've concluded that the null is false. In this particular case, you're okay and you found power. Very, very important for us. So here again, out there in the real world, the null is false. You concluded that the null is false. You have found power. Now, very important, when we think about this, essentially here we're saying that we're trying to do the following. To find power, we want my statistic to land inside of this region here. I want my stat to land here, okay? If my statistic lands in here, so here's my critical value, the beginning of my region of rejection. If my statistic lands in here, and it was supposed to land in here, I have a type 2 error. If my statistic lands in here, and it was supposed to land in here, I have a type 1 error. If my statistic lands in here, and it's supposed to land in here, I have power. If my statistic lands in here, and it was supposed to land in this area, I am okay. All right, so let's get into talking about our last issue for this week. Our last issue is the issue of power. Since we've already started talking a little bit about power and talking about what power is and what power isn't, remember that power is the probability or the ability to find a true effect. So in other words, how do I actually maximize my ability to have my statistic land in the region of rejection if it's supposed to land in the region of rejection? Now, before we begin talking about power, there's just a couple of other things that I want to talk about before we get into this. Now, one of the things that we need to think about is how inferential statistics work. And pretty much all inferential statistics work in the exact same way. We have effect variance, which again, remember, is the amount of variability that is being explained by systematic group differences and or relationships among variables. Another way of saying effect variance, differences between our scores that are due to the researcher's manipulation or control. So in other words, the difference between group 1 and group 2 is due to my manipulation or control, right? So they are different because I've made them different. Thus, they have different scores because of my treatment. Error variance is the amount of unexplained variability not explained by systematic group differences and or relationships among variables. So in other words, differences between my scores that are not due to my researcher's manipulation or control. So when we think about statistics, all statistics, inferential statistics, work in the same general format or the same general formula. All inferential statistics are made up of the following: effect variance divided by error variance. So even in our current example here that we were working with our z-score, remember that with z, we were talking about the difference between my mean and the population average divided by standard error, right? Look at the difference between these two values. So my mean, my manipulation, my control, and the population mean. So in other words, differences between my scores that are due to my manipulation or control, effect variance. Denominator, error variance. Because remember, I told you standard deviation, variance, range, and even in this case, standard error, which is a measure of variability, is going to be a measure of error variance. Because remember, our formula also for z was our score minus our mean divided by standard deviation. Again, effect variance, differences between my scores due to the researcher's manipulation or control, and error variance. There we go. So when we think about even this formula for z, this is the same general format for all statistical tests. So ultimately, when we think about power, power can be influenced by 6 particular factors. And I'm going to talk about those 6 particular factors in just a minute here. So let me just erase this very quickly. Okay, so when we think about how statistics work in terms of fractions, in terms of our numbers, the higher the error variance, the lower the error variance, the larger the stat. So the larger the effect, the lower the error, the larger the stat. So in other words, think of an example like 1 divided by 4, 2 divided by 4, 3 divided by 4, and 4 divided by 4. You'll notice that in every single one of those instances, we have our number increasing in the numerator and our denominator remains constant. So here 0.25, 0.5, 0.75, and a value of a 1. So ultimately, I want more effect variance and error variance to remain constant so that way my statistic becomes larger. The larger my stat, the higher the likelihood that it's going to fall into the region of rejection. Now, when will your stat decrease? My stat will decrease if my effect variance decreases and my error variance increases. So let's now go here with the same format here if you want to think about it in this particular case. Now we're just going to go in descending order here. So here 4 divided by 4, so I have a large numerator, large denominator, same number with a 1. Now my numerator starts getting smaller, but my numerator starts getting larger. So 0.75, 0.5, 0.25. So now you'll notice that my stat begins to decrease as my numbers begin to go down in terms of the numerator. So what I want to do, I want to try to have this occur. Have as much effect variance and as little error variance as possible. Why? So that way my stat can be as large as possible. That would be the ideal situation for us. All right, that's what we want to try to do. So increasing power, how does power actually increase? So if you were reading along in your textbook and you were approaching section 8.6 in your textbook for statistical power, you were probably by this point getting pretty tired and you were saying, all right, it talks about power. I don't really know about power, whatever. This is what I want to talk to you guys about power. There are specific factors that affect power, and there are 6 factors in particular that are going to affect the power and the likelihood that your statistic is going to land in the region of rejection if it's supposed to land in the region of rejection. Because remember, power is the ability to find this true effect. So in other words, correctly rejecting the null hypothesis. So if I'm supposed to reject the null, I want to reject the null hypothesis. So this is the probability that the test statistic is going to fall in the region of rejection if it's supposed to fall in the region of rejection, which again is what I want it to do. So there are 6 particular factors that are going to influence power. What are those factors? Number 1, the size of the difference or the relationship, or what we also call effect variance. Size of the variance. And in this particular instance, we're going to call this error variance. Oops, there we go. Alpha level, sample size, the nature of the null. So in other words, is it 1 or 2-tailed test? And last, the type of design. Is it a between or within groups design? So this is what I want to talk to you guys about just for the last part of our class. So in terms of number 1, effect variance. So let's begin with effect variance. How does effect variance affect my power? Well, remember, think back to our previous slide here, that we were saying here that the larger the effect variance, the larger the statistic. So the higher this number is, the larger the stat. So how do I increase effect variance if that's something that you're thinking about? So how do I make that happen? How do I make the differences between my 2 numbers be larger if I can get them to be larger? The way that this happens is through the following form. If I want my score to be different from another score, I want to make sure that the manipulation that I include for them is extremely different. So let's say, for instance, I'm comparing high stress and low stress individuals. Okay? So here, what I want to do is I want to measure them on their memory. So out of 10 items, I want to see what the average number of words recalled for high stress is and the average number of low stress words recalled are. So what I find is that for high stress, they remember 2 out of 10 words, and for low stress, they remember 8 out of 10 words. So perfect. Here now, I want to look at the differences between those two groups and see if I'm going to reject or retain the null, right? That's going to be my goal. So reject or retain the null hypothesis. So now here, how do I ensure that these numbers are extremely different from each other without changing the scores myself? Well, I'm going to do this by including my manipulation or my control. In other words, I'm going to try to make my groups as similar to each other as I can on the individual basis. So in other words, I'm going to try to make sure that if I have 5 males here, I'm going to have 5 females here. Or sorry, 5 males here, 5 males here. 5 females, 5 females. 18 to 20, 18 to 20. From San Antonio. Everything starts becoming more and more similar between them. So at that way, the only thing that is different between my groups is my manipulation or my control. In other words, the high stress or the low stress. So now even here, how do I make sure that the high stress is actually high stress? Well, we're going to do extreme manipulations. So for instance, a participant walks into the room, and as soon as they walk into the room, we start yelling at them. Hey, come here, sit down, and we start throwing papers at them to fill out. And then we start putting thrash metal in the background that's way too high at an intensity level. So here, it's very, very aversive to them because it sounds way, way too loud for them. So it starts hurting their ears and becomes almost painful. We start turning off the lights and on them, and it starts freaking them out. There's weird smells in the room, and it stresses them out. So here, our stress manipulation is very, very intense. For the low stress sound, or for the low stress environment, people come in, we greet them with namaste, there's candle smells in the background, we make them sit on beanbag chairs, we're very comfortable with them, we speak to them in a very professional fashion, very, very soothing environment for them. So now here, if we do find differences between my groups, I'm going to assume that the differences between my groups are due to my manipulation and my control. So ultimately here, if I have those extreme manipulations, which I think are supposed to have an effect on my results, that's how I'm going to increase effect variance. The differences between my groups that are due to the researcher's manipulation or control. Number 2, error variance. Trying to minimize error variance. So again, I'm trying to have this situation right here. I'm trying to have the situation where I increase effect, lower error. How do I lower error variance? Again, I try to make my groups as similar to each other. I try to make sure that I have 5 males, 5 males, 5 females, 5 females, San Antonio, etc., etc., etc. Minimizing individual group differences. That's what I want to try to avoid. So here, minimizing error variance, maximizing the control that I have in a research situation. Third factor that we talked about, alpha level. We've already talked about alpha level and how it can affect power. Here I'm going to go back to my notes that I was providing for you here in terms of the differences between a high alpha level and a low alpha level. Remember that as I decrease alpha level, what happens to my region of rejection? Well, as I decrease alpha level, my region of rejection gets smaller and my critical value gets higher. So in other words, as alpha level gets smaller, this area for me to be able to reject the null hypothesis starts getting smaller and smaller and smaller. So as this area starts getting smaller, it starts minimizing my ability to find power. Think of the following. Think about having 2 bottles. One bottle is the size of a soda bottle opening, which is a very small opening, and then you have a trash can. So the opening is very, very wide. And what you're going to do is you're going to throw a tiny little piece of paper into either the bottle or the trash can. So the size of the bottle opening and the size of the trash can opening are the size of my regions of rejection. So if I'm telling you, hey, I'm giving you 5%, I'm giving you the size of the trash can opening as your region of rejection, wouldn't you want to take that? Wouldn't you want to maximize the probability that you're going to throw your piece of paper into the trash can? Yes, right? You would absolutely want to do that. You would want to maximize the probability of you having your paper land into the trash can, into that receptor, because you have such a wide opening, because we're allowing you that. But here you say, well, no, I want to make this really, really hard on myself. I want to minimize the probability of me making a mistake, and here I'm going to make the opening very, very small. So here, if I do land in that region, I'm going to be very, very confident in my abilities to make that shot. But here, you're decreasing the likelihood that you're going to make the shot because you've given yourself such a small opening to be able to reject the null hypothesis. So here, it's much more likely that you're going to miss and you're not going to reject the null hypothesis. So in other words, you should have rejected the null hypothesis if you would have had a wider opening, but you didn't. So here, that becomes problematic for us, and it potentially leads to us having type 2 errors. So which of the two is going to be more powerful? Which one is going to increase power? Having a larger alpha level is going to maximize power because it's going to give you a wider area to reject the null hypothesis, as we have here with our red critical value. With our blue critical value, I still have a region of rejection, but it's now tougher for me to reject the null hypothesis. So which one's more powerful? The more powerful test is going to be having a very high alpha level, the most that we can potentially give you. In this particular case, having an alpha level that is maximized at 0.05. That's why we continue to select 0.05 as the maximum alpha level. Number 4, sample size. This one's a tricky one. Sample size is a tricky one because the way that it affects our particular situation in terms of our Z distribution is very interesting. So remember that for the formula for Z in this particular case was the sample average minus the population average divided by standard error. Now, if you remember back to the formula for standard error was the following. Standard error was calculated by taking your standard deviation and dividing it by the square root of your sample size. So here, let's say that your standard deviation again was a 20 and your sample size was equal to a 25, right? So here, this would lead you to having 20 divided by 5, giving you a denominator equal to a 4 in this particular example, right? But now let's say that we're going to increase my sample size. So we're going to go from 25 to 100. So standard deviation remains the same. Now I have 100 participants that I'm going to have in my denominator. And now we should now give me a value equal to a 10. So when you take the square root of 100, that should give you a value of a 10. 20 divided now by 10 should give you a value of 2. So now my denominator has gotten smaller. So now having the smaller denominator, again, remember, in terms of how we actually calculate power, that my denominator is going to have a major impact. The smaller my denominator, the larger my statistic. So again, here, increasing sample size, in this particular case for Z, is going to decrease my denominator for my formula in this particular instance. Now, another thing that happens for us whenever it is that we actually look at this issue associated with power and sample size is the following. That's a terrible sample distribution. See if I draw a nice one. Okay, about as good as it's going to get. So remember here that the average for this distribution was going to be equal to a 0, right? And we assume that this is going to be representative of the population, okay, in this particular case. So now what happens in the case where we have an increase in sample size? As we increase sample size, this is what ends up happening to my distribution. Okay, give me 1 second here, guys, sorry. As sample size increases, you'll notice now that the distribution starts getting taller and thinner. And I'm going to keep drawing these. So as sample size increases, my distribution starts getting taller and thinner. Why does this happen in this particular case? Why is it that as my sample size increases, that my distribution is going to get taller and thinner? It happens for the following reason. Remember that this line here represents the population. So it's going to assume that we're going to have everyone from the population being represented, and if we have everyone from the population being represented, our line is supposed to be representative of the distribution. But yet that doesn't happen. So what happens? As sample size increases, we start pushing in the distribution to start mimicking this line, because we start getting more and more and more of the people to represent the population. Thus, we start pushing in that distribution into this line, pushing in all our numbers, getting everything closer to zero. So thus, as sample size increases, my critical value decreases and gets closer to zero, and my region of rejection gets larger. So in other words, as this distribution starts moving in and in and in and in and in, remember, alpha level remains the same. So let's say that alpha level was set at 0.05, and we have a one-tailed test. Everything remains constant. The only thing that changes is sample size from 25 to 100 to 200, etc. We now start pushing in this distribution. So everything else remains the same. The only thing that increases is sample size, thus bringing in my distribution closer into this line here that represents the population, thus creating smaller critical values and a larger region of rejection. So here, how do we increase power with sample size? Increase sample size. So have sample size be as large as possible so we can bring that distribution in closer to that zero value. So here, just to show you another example of how this happens, this is the critical value sheet for T. So this is a distribution that we're going to be talking about, a statistic that we're going to be talking about in the next couple of weeks. But one of the things that you'll notice about this critical value table, it's very similar to the one that we were using for the normal distribution. It just changes a little bit. So here, for instance, I'm going to say that I'm going to look at an alpha level of 0.05 with the sample size equal to 25 and a one-tailed test. Now here, you guys are just going to have to trust me on this for now, and we're going to talk a little bit about this later on. But here you'll notice that we have degrees of freedom. This is correspondent to our N total minus 2, okay? Degrees of freedom, remember when we calculated standard deviation, in the denominator we calculated N minus 1. But remember, I was just talking about earlier in our lecture that we do this for every single group. So I do this for group 1, and I also do this for group 2. So for group 1, I take N minus 1. For group 2, I take N minus 1. So thus, if I add up their sample sizes, I have N total minus 2, because here T is assuming that I'm working with two groups. So we take 1 from group 1, 1 from group 2, leaving me with N minus 2. So here, degrees of freedom, we're going to go and find N total, which is 25 minus 2, which is a value of 23. There we go, for degrees of freedom. So we're going to go find 23. One-tailed test, 0.05 alpha level, gives me a critical value of 1.71. But now you'll notice that if I go now to sample size equaling 100, which would give me degrees of freedom equaling 98, I now go down to here. I'm going to go to 90 because I like to be a little bit more conservative. I like to be closer to 90 than to be 100 because I don't have 100, but I have 90 at least. So degrees of freedom 90, you'll notice now that the critical value looking in the same column is a 1.66. So you'll notice here that as sample size increased from 25 to 100, the critical value here drops from 1.71 to 1.66. So this is a core example or a primary example of what happens to that distribution. So as that distribution starts getting more and more people, it starts getting taller and thinner, so in other words, becoming more kurtotic, until it finally represents that line there that we talk about in terms, as best as I could draw my line. Sorry, my line drawing is off today. There we go. Representing that line that represents the population performance in that particular case. Now, the last thing I want to talk about, we have just a couple of more issues that we have to think about. Number 5 is the one versus two-tailed example. So I've already talked about this issue also of one versus two-tailed. So I talked about it here when we were trying to find our critical values. And I was showing you what happens when we go from a one to a two-tailed distribution. So remember that when we go from a one-tailed to a two-tailed distribution, on a one-tailed distribution, I'm allowed to give all 5% to that one single critical region. But if I go to a two-tailed test, I now have to share that 5%. I have to now share 0.025 and 0.025. So 2.5% and 2.5%. So here, by going to a two-tailed test, you're going to notice now that we have a smaller critical region, and it's going to make it less powerful for me. So which one is going to be more powerful, a one or a two-tailed test? Technically, a one-tailed test would be more powerful. Why will a one-tailed test be more powerful? Because it allows me to have all my alpha level given to that one region of rejection. Now, in the case where we have a two-tailed distribution, I now have to share my alpha level per region of rejection. So each one gets half of that alpha level that I've selected. So thus, with a two-tailed test, I have lower alpha level. My critical value is further away from 0, thus giving me a smaller region of rejection. Okay? And that's very, very important for us again. So again, remember, with the two-tailed test, I have critical values that are larger. My region of rejection gets smaller, and my alpha level gets smaller per region of rejection. So ultimately here, what do I want to do? I want a one-tailed test. Now here, I've been telling you though, one-tailed test, very risky. This is all risk. And it is, but it's more powerful. So here, which one do you pick? What's my favorite answer? It depends. What does it depend on? Well, do you want to take the risk and have a more powerful test? Do you want to be conservative, have a less powerful test, potentially miss an effect, but then you can always redo it and do a one-tailed test? Because remember, in the case where you have a distribution where it's a two-tailed test and your statistic lands just right out here in a two-tailed test, you can go back and do a one-tailed test, and now your statistic lands inside the region of rejection with a one-tailed test. So this is a one-tail. So here you can always go back and redo your statistical analyses and modify to having a more powerful test the second time around. Now the last issue here that we're going to talk about is this issue of design type, what we call a between versus a within groups design. We talked about this at the very beginning of the semester. Now we're starting to talk about research methods again. Why? Because it's important to make this link between research methods and statistics. It's vital for us to have success in statistics. We need to have an understanding of research methods. From here on out, I'm going to be talking a lot about research methods. So it's essentially going to be a combination of your research methods class that you're going to take in the future and also statistics. Now in this particular case, why is it that the between or within groups design plays a huge role for us in terms of power? Remember that with the between groups design, we are having different individuals participate in each one of our groups. So in other words, in group 1, we have 5 random students. So this is group 1, and we have person A, B, C, D, and E, right? In group 2, we have F, etc., 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 right? So we have different participants. So if we have different participants between group 1 and group 2, naturally between the two groups, we're going to have natural error variance, or what we've also been calling sampling error. So in other words, naturally there's going to be differences between these individuals and these individuals. Why? Well, because these individuals are different from these individuals. This is a between groups design. So in other words, people in group 1 are different from people in group 2, thus creating natural error variance. If I have natural error variance, I'm going to be increasing my denominator in my formula, right? So remember, because my denominator is going to be error variance, right? It's representative of that aspect of error variance. So here my denominator is error variance. With the between groups design, having different individuals between my groups is going to create natural error variance, thus increasing this number, potentially leading to a smaller statistic. So how do I combat that issue? I combat that issue by having a within groups research design. So in other words, what I'm going to do is, rather than using different individuals from one group to the next, I'm going to use the same individuals. So here group 1 is going to be made up of A, B, C, group 2 made up of A, B, and C. Why would I want to do that? Well, because here, group 1 and group 2, even though they receive different treatments, they are the same people. Since they're the same individuals, we should have less error variance. Now, I say we should. That's not always the case, because there may be other factors that may contribute to error variance that we may not be in control of. And as the semester progresses, we're going to talk about some of those issues as well. But here in a theoretical world, we're using the same individuals, so thus we should have less error variance. So here, between group testing number 1 and group testing number 2, you should have not had seen the light at the end of the tunnel. You should have not had an epiphany. You should have not had any major events in your life that could have potentially changed you at some level that may affect my dependent variable, especially if the difference between group 1 and group 2 occurs in 5 minutes. So I tested you at 10 o'clock. At 10:05, I give you part 2 of the test. So here you should have not seen any of those issues occur. So you really shouldn't see any differences between the groups because of error variance. If you do see differences between your groups, it's going to be due to effect variance. Okay, so in other words, it's going to be due to differences between the groups due to my manipulation or my control. So of the two, which one's going to be more powerful? A within groups design, not a between groups design. More powerful within a one-tail test, not a two-tail test. Sample size, higher sample size provides you with a greater powerful test. Alpha level, higher alpha level. So maximize, right? Set at 5%. Don't go to a 1% or a 2%. That's too low. So here, it's good for you to do that, right? Because it increases the confidence of your results if you do reject the null hypothesis, but it gives you a less powerful test. That's why I was saying it has consequences. Size of error variance, decrease error variance, right? So decrease error variance. And last, size of the difference, increase effect variance. So here, ultimately, I want to maximize power. I want to try to maximize my ability to find a true effect. I know that this lecture has been extraordinarily long. Don't worry, I am well aware of that because I recorded it, so I know it's been extremely long. But this is all very valuable information, guys, that you are going to be using for the remainder of your statistics, research, and professional careers. I guarantee it. Every single day when I do anything that revolves around research, I'm thinking about all the issues about null hypothesis significance testing, power, my designs, etc., 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 because this is pertinent information. It's critical information for us to understand how this works. If you guys understood this lecture and how I came to the conclusion about rejecting and retaining the null and understanding power, you have understood all of statistics, guaranteed. Now all that we're going to do for the remainder of the semester is introduce new statistical tests, talk about their benefits and their limitations, talk about when we would want to use them, and then refer them back to this aspects of null hypothesis significance testing and power. Okay, my recommendation, read your textbooks, go over the lectures a couple of times to really help cement that information. Please make sure to turn in your homework assignments. You all may have noticed that this homework assignment did not give you any questions from the chapter because I don't like any of the questions from the chapter. I made up my 3 questions for you for this week. So please make sure that you do look over the chapter and look over the lectures before completing the homework assignments. Please also make sure to complete your discussion board post by Friday, and then your repost or your comment post to somebody else's post by Sunday by 11:59 p.m. Also, just a reminder, we do have our exam coming up the next week. So next week we have our exam. Again, just as I've done with the first exam, I will provide a review sheet, provide a little mini review lecture, a very brief 20-minute lecture to kind of help you guys review. And I will include all that information by no later than Wednesday of this week. Have a good rest of your week. Make sure to cover as much information as you guys can over this lecture. I will make sure to include this PowerPoint so that way you can print and you can follow along. I will also include my notes page here that I made, and I will include this in Blackboard for you. Have a good rest of your day. Enjoy your week as much as you can based on what it is that I've talked about. And please let me know if you have any questions.